All right, good afternoon, everybody. Great to see you all. So this is the class on programmable photonics for quantum networks. And I'd like to acknowledge first Chen Ji Jin, who's a PhD student at Harvard University, working there with one of our other team members on the program, Professor Marco Lonkar. And it's been great working with CJ on putting together these slides and the interactive exercises, which will happen through Jupyter Notebook in a way that should have been shared already with you before. I also want to acknowledge other people, in particular, Mike Raymer, who has been on our case to make sure that we get everything in on time, and all the admin team at the CQN. So excited to talk to you today about this topic, which is pretty good overlap with the research area that I am tasked with in this overall program on Center for Quantum Networks. So I see people still joining. I will just get started now, I think. CJ, do you have anything to add before we get started?
Yeah, so the link to launching the Jupyter Notebook, I will drop it in the chat. If everyone can see the messages in the chat.
Yes, you'll be able to chat out.
Okay, great. All righty. Okay, so let's get started. I kind of want to set the scene a little bit here in the beginning about why we need this new generation of what I call programmable photonics. And the best way I can describe it is that there's a new set of demands on optical systems that's particularly driven by sort of a renaissance in computing. Quantum computing is an example of this. So for decades, it's been fine to just make computers whose basic architecture was really invented already back in the 1940s and 50s, just to make these computers more and more powerful by adding more and more switches, more and more transistors per area. But that scaling is running its course, and moreover, there's interest to see if we can address certain problems that type of architecture, the classical von Neumann computing architecture, probably will never be able to address. Certain classes of problems that are known to be exponentially hard, meaning that even for a modest sized problem, that type of computer, the best supercomputer, even in 20 years, would take millions of years to solve. So are there other types of computers, other ways of using physical systems to compute that may help us address some of these very gnarly problems? And there's in particular two areas in which photonics is finding a great demand. And these are the ones that really are motivating a lot of the work that I'll talk to you today about. One of them is in quantum computing. And so in quantum computing, you've seen over the last years, tremendous amount of progress. Google in 2019 claimed that they had reached what they called a quantum supremacy, a milestone of a certain type of algorithm, a sampling problem on a circuit of superconducting resonators coupled to nonlinearities that could do certain things, in particular sampling the output of that processor to sample distributions that were difficult that are exponentially difficult with a classical computer to calculate. And so that's one example. There's another. These are actually both photonics. This one happens to be microwave photonics in the roughly 10 gigahertz range in the superconducting device. But there have been also several claims of what nowadays is better referred to as quantum computational advantage, using optical photons. So here, for example, is a device developed by the team of Professor Zhenwei Pan in China that performs also a sampling problem, in this case, on an array of squeezed optical fields that are measured after coupling with one another through this large multimode interferometer on single photon detectors. The other areas, I should say for completeness, are in, for example, quantum simulation, where perhaps you'd like to predict how certain materials behave that have a great deal of quantum correlations within them, where the properties, the extrinsic properties of the material, depend on the quantum mechanical interactions and correlations of electronic states, for example, like in a superconductor. And that problem, predicting good superconductors, for example, is still an elusive thing in high temperature superconductors. And so the question is, can we map the physics underlying that correlated electron system onto near-term intermediate scale quantum devices like ultra-cold atoms, perhaps, to try to predict what is a good material and what isn't, or at least to gain a greater understanding, even if it's not quantitatively accurate, to gain a better understanding of how these phenomena come about, these macroscopic entanglement-derived phenomena come about, and then maybe be able to one day predict what are the right materials, rather than a lot of guessing at the moment. The second renaissance in computing that also puts more and more demand on optical systems is the area of machine learning. Things like signal processing and self-driving cars, natural language processing, protein folding, and so on, have made tremendous headway. And at the same time, that puts tremendous pressure on traditional computing system. And so there's a great hope that optical systems will not only help in the communications part of machine learning, training and inference machines, but also in the, but maybe can also take bigger roles, like beyond communication, they should do some of the computing itself. So it's these things that have motivated my group to develop new kinds of optical systems. And here I'll certainly I'll give you some glimpses of stuff that's going on in my group, but I should say that this is really a broad, global effort, and I'll do my best to give you the complete picture as we go along. I just want to, since that overall view was rather broad, I want to give you just a more concrete glimpse at the problem, let's say in one area, and might as well pick one. Let's pick in quantum computing because it's closely connected with quantum networks. Indeed, the quantum computer will, I believe, require quantum networks, and quantum networks will require quantum computers. In many ways, they are two sides of the same coin. And so to take a look at the kind of challenges we're asked to solve in these programmable optical systems, I have a chart here that shows different kinds of quantum computing architectures, approaches that have different amounts of requirements on optical systems. On the left-hand side here, we have quantum computing systems in which the quantum information resides at all times in the internal state of trapped ions, or perhaps the internal state of neutral atoms that are laser cooled to far sub-Kelvin temperatures, and that are interacted either in the case of ions by Coulombic forces, or in the case of cold atoms by, for example, Rydberg interactions, by basically blowing up moving the electron to an almost ionized large N orbital, so that dipolar interactions between these Rydberg atoms can cause strong interactions at several microns of distance. Shown here, for example, is a picture, a photograph of single rubidium atoms at ultra cold temperature, about 10 or so microkelvin, with a spacing of several microns. That spacing is smaller than needed for strong coupling between these so-called Rydberg states. In both cases, however, it's necessary to interface with these atomic systems optically. There are no wires connecting to these ions, no wires connecting to these neutral atoms. They are in a vacuum, and the way that we initialize, manipulate, and measure them is through laser fields. So, and even though laser technology has come a great way, so that nowadays you can, on a single spatial mode, control the classical field very accurately, and thus control the atom with low error, it's still impossible to do that with many simultaneous degrees of freedom, so that you could address many individual qubits, atomic qubits, ionic qubits, with individual programmability. So this is where this word programmability comes up, is you want to be able to program this atomic system with high fidelity and at scale. And for this, you need a new generation of optics. It doesn't exist today that allows you to project high precision laser fields at every one of these sites. So this demands a new kind of laser system that allows you like something like a gigahertz or so modulation, on-off modulation rate, but also with very high contrast. To keep errors low, you want to have the contrast and the intensity be something like 60 dB. So there are no commercially available modulators that can get to 60 dB. Electro-optic modulators, you know, when you buy them for telecom applications, they might go to 20 dB if you're looking for the high-end stuff. Maybe they go to, you know, around there. So, but you need to go to 60 dB, right? So, and oftentimes just stringing one after the other isn't good enough. So it requires very precise multi-mode coherent control. That's one area for these programmable optical systems. Here is the quantum network that's like the quantum network that we're developing in the CQN. Here you have quantum information residing for longer time durations on the atomic memories, just like before, but the optics does a bit more lifting here, because photons actually shuttle quantum information in the form, in our case at the moment, of single photons between these atomic quantum memories to establish what's called a quantum network of networked memories. And so here, there's even greater demand on the optical systems, because not only do you have to modulate with the similar kind of precision for the gates, because these atoms are also controlled using these optical gates, but you also need to worry about optical losses. So you need to, in addition to here, where maybe your optical losses aren't so important because you're just using the optics for controlling these systems, here you also have to keep losses low so that photons scattered from, or optical fields that have interacted with one atomic qubit have a reasonable chance of making it to another distant qubit to spread entanglement that then serves as a resource in these kinds of systems for general purpose quantum computing. Okay, but I said that the networks and quantum computers are really probably two sides of the same coin, and the reason is that here you see the size of this kind of a quantum computer based on ions or perhaps on neutral atoms will be limited by how many of these you can stuff into a box, into the quantum computer. And then you will, just like we have to with present day computers in data centers, have to network them. And so there you will actually have a network like this, but rather than having each of these represent a single spin, perhaps a single qubit memory, these networks will actually have to connect quantum computers together. And indeed, the same coin, two sides. Alternatively, looked at a different way, the quantum network to be able to scale will require that these nodes be very sophisticated. They can't just be single quantum memories. They need to be small error-corrected quantum computers if you want to be able to scale this to very large networks. And so really, there's really a convergence between these fields of these atomic quantum computers and quantum networks that will at one point or another have to happen. There are other ways, if you can make the optical control even better, that are being pursued in the industry and in academia and academic research and government research. And in that case, the photons do even more of the heavy lifting. Not only do they shuttle, albeit imperfectly, quantum information from one memory to another, they actually have to perform logic gates here in two different ways. One way that's being pursued is to use matter only temporarily, like a few atoms in a cavity coupling to an optical field, to mediate entanglement between quantum information that's actually stored in the optical field. So this I would call photonic qubits that are assisted by atoms or bulk nonlinearities. Actually, CJ works on something that's quite related to that. If the kind of photonic integrated circuits that CJ and her team with Marco become better and better, there's a chance that you can do exactly that. If these lithium niobate mediated three-wave mixing nonlinearities become very efficient, you could actually do these kinds of approaches where one of the benefits is that they could work at room temperature. And then finally, an approach pursued, for example, in industry by PsiQuantum and by Xanadu is to use measurement-based gates, where you use optical heralded gates, heralded by probabilistic but heralded measurements, to create a sort of a mesh, a cluster of qubits encoded here in optical modes that can then serve as the resource for doing general purpose quantum computing. That's probably the most demanding approach for optics because it requires so many modes. But you see here the spectrum of applications for which there do not exist at the moment sufficiently good and scalable platforms for programmable optical fields. And so that's sort of like what we're going to look at today. And when you develop these, you can't think in isolation. Oh, I just want to make something with a really good transmission. And no, you to address these really hard problems, it really requires a co-design. You have to consider how the algorithms connect to the photonic control and how the photonic control connects to the hardware on which it's running, like the photonic circuits and the electronic and the electrical control. So that's sort of like an overview of what we're going to be talking about today. And at this point, I want to encourage people once again to just come up, raise any questions that we could answer along the way. Let's see here. No, so far, no questions asked. Let's see if there's any questions from the participants. If not, I'll keep going. So I showed you now where we want to get to do these awesome things. We have to do our homework first. So let's begin, just so that we're all on the same page, with a brief review of what actually the quantization of the optical field is, because that's very important to speak the same language, to speak the language of quantum optics when designing optical systems that are supposed to serve some role in quantum systems. So for many, this will be a review, but certainly not for all. So I figured I would give you sort of just a very quick run through of what we actually mean by the quantization of optical fields, or in other words, photons. Where do these photons actually arise from? Where is this idea from? Why do we need this idea of photons? This is also called, so one term for this is called the electromagnetic field quantization. And we're going to look at this in a single mode case in a cavity. This is sort of the simplest scenario to consider it. But once you understand how to quantize the electromagnetic field in a single mode, since all of space can be described as a superposition of many modes, and if you can describe a single mode, then using linear algebra, by and large, you can describe all of space. Okay, so it's sufficient to just understand how it works. So single mode is easy then to extrapolate to that, to a general picture. This also is called second quantization, which has a historical origin when after the mechanics in quantum mechanics was quantized, people started to think about how we can apply, how one can like look at the quantization of fields. And that is why it's called the second, just sort of like historically, one after the second quantization. Okay, so to this end, let's consider a simple electromagnetics problem. We have here on the top right-hand side, two mirrors that are metallic and assumed to be perfect conductivity, so there's no loss. And therefore, the electric field, all electric field components on the surface of that mirror have to go to zero because the conductivity is high, therefore there can be no electric field inside the mirror. So the electric field has the boundary conditions that E at Z equal to zero, and this is our coordinate axis, Z equal to zero here, so on that mirror is zero, and E at the other end at Z equals L is also equal to zero. And all right, so at this point, there can be multiple modes that satisfy that boundary condition, but we're going to pick just one polarization states. Okay, but in general, the electric field can be written in the following way. The electric field at a position in space R, of course, is a vector field. So this E is a vector at a position, which also is a vector. And in time, if you want a full vector, is equal to some superposition of modes indexed here by J. Each mode, when we use the word mode, that is a single, that is a solution to Maxwell's equation. Okay, it's a superposition of modes that are indexed here by J, and they have a spatial distribution F sub J, and they have a time dependence here, assumed to be separable, Q sub J of T, and then there is some amplitude C sub J associated with that mode in the overall summation of modes. Okay, so in this case, because the setup is pretty easy, we can we can just many of you will already know the solution of the mode set, and that is that the F sub J is equal to sine of some coefficient K times Z. Z is along the axis of the cavity, times some position unit vector X. So we're going to consider here only one of the two polarization states of the possible solutions, the other one being Y hat, but we can assume that there exists a polarizer in there so that we can just consider, like, the system here is filtered to only allow that single polarization state to persist. All right, that thing here is multiplied by a time, by a function Q, that for that particular J gives it the time dependence. And then there is a normalization factor out here. We bring that guy in because we demand that the integral of the mode squared is unity. All right, once I've written down the form of the electric field, just applying the curl and the time derivative from Maxwell's equations, we can solve for the magnetic field. And I've done this here, and that would be the expression of the magnetic field here. Okay, at this point, we have a general solution of all of the electromagnetic field of this cavity, which once again, we've assumed to have only one polarization in the x-hat direction. Now we can calculate the energy in that field. That comes from, just integrating the energy density that exists in the electric and the magnetic field components. And that's also the classical Hamiltonian. If you like the the Hamiltonian, if you think about the Hamiltonian of that system, and that is equal to the integral over the volume of the energy density here. Epsilon naught, we're assuming that this is in vacuum, times Ex squared plus mu naught times Hy squared. Why Hy? Because we're assuming that the system is in the X hat direction polarized for the electric field, and therefore from the curl, it means that the magnetic field must be orthogonal to that. It's also orthogonal to the z-axis, therefore H has the only component that's non-zero for the magnetic field is the y hat component. Okay, and now this here is, and this is what people noticed back then before they did the second quantization, this thing here is mathematically identical to a mechanical thing. Okay, so people had already quantized the mechanical motion of an electron, for example, in a harmonic potential. Okay, so they were well familiar with this expression, and they were like, wow, look, mathematically, this is exactly the same expression as for a classical harmonic mechanical oscillator, right? Because that has a potential. There, the energy is equal to the potential of the potential energy stored, which is 1/2 k q squared, and the kinetic energy, which is 1/2 times q dot squared times m. Okay, so this looks just like that, doesn't it? In fact, it's mathematically identical. So we can basically recast it in a way that mathematically people had already gone through the effort of quantization, and then we will have succeeded in our quantization of the electromagnetic field. So the Hamiltonian here to this end, let's express these quantities as let's introduce here these so-called conjugate observables that satisfy the Hamilton-Jacobi equations, as you do in deriving the Hamiltonian, and so this normalized operator here, Q sub j, is equal to m sub j times omega sub j divided by h bar times q hat, so then the Hamiltonian that's written here, which associates the Ex component with Q and the Hy component with Q dot, with the velocity, can be written here in this form in terms of normalized operators. There's normalized momentum operator P sub j squared plus the position operator Q sub j squared normalized. So this whole thing divided by 2 times h bar omega j is the energy of the harmonic oscillator. Now what we have to do in the quantization of the field is we're going to relate the electric field components that we had in the Hamiltonian to these operators. And to this end, it's useful to introduce two additional operators that they're going to be using throughout this course to describe quantized electromagnetic fields, and they are: one, the lowering operator or the annihilation operator for mode J, A sub j equal to Q j, okay, the position operator for that oscillator, plus I times P sub j. This is just a definition. Just take it for now, and we'll see where it goes. And there's the raising operator, which is just the Hermitian conjugate of the lowering operator. Okay, so now we can write the Hamiltonian, which also is a Hermitian operator, in terms of these raising and lowering operators instead of in terms of P and Q. And here it is. I go through here this math, and at this point we could actually, let me just show you sort of how an important part here in this step. So you know from the first quantization that these commutator relations apply. That is, this states that it's not possible to measure the position and the momentum of a single quantum particle at the same time, okay, if they are the same. So Q sub j comma P sub j is equal to I h bar delta jj being 1. So, and this results, if you just remember your quantum mechanics, that this demands that if we look at the Heisenberg uncertainty principle, for example, that it's impossible to measure each of these quantities simultaneously with arbitrarily good precision. Okay, so this is here from the first quantization, but we can rewrite this now for the field operators. We can rewrite these commutation operators for the field operators. How do we do it? Okay, so plug in here, like if you look at Q, for example, let's do Q sub, let's say that they're the same index, and I'll drop the index for the simplicity of writing it, Q and P. Commutator is equal to, all right, so let's see, we can plug in here, we can solve here for Q and P in terms of the raising and lowering operators. We can do this by just summing over these two, so it's A plus A sub j. Okay, if I sum this plus this, sorry, A sub, assume that both of them are talking about the same mode, so that both of them are j already. I'm just not going to carry that over, but the implication here is that both of these are going to be the same mode. If otherwise, they will commute. Okay, A plus A dagger is equal to, okay, so we're summing this plus this. That means these guys cancel out, and we have 2 times this. We have square root times Q. Okay, let's divide the square root out. And this here is equal to Q. Okay. And similarly, if we subtract A and A dagger, A minus A dagger divided by root 2, if you do this again, this is straightforward at this point. This gives you, so A minus A dagger gives us an extra I here, so this is times I is equal to P hat. Okay, so now what you do is take these two, plug them here into this commutator expression that we have given to us from the first quantization, and then you can plug and chug and find that this is the case, that the two operators that we've introduced here, the lowering and raising operators, also do not commute if they are applied to the same electromagnetic mode, i.e. the indices here are equal. But they do commute if the two modes are different. So I see. Yeah, so A and A dagger do not commute if J is equal to I, but A and A dagger and A do commute. All right, so at this point then, now that we have this out of the way, we can plug in our expressions for P and Q, now in terms of A and A dagger, into this equation here. And now there's a little bit of algebra that we can do together in a moment to derive this expression, which expresses the Hamiltonian, the energy of the electromagnetic system, as in terms of these raising and lowering operator summed over the energy of every mode J over all modes J that comprise the electromagnetic field. Okay, and then finally, now in connecting this to the P and Q terms on the previous page, we can write an expression, at least now for time equals 0, of the electric field operator. Now this is an operator, importantly, at any point in space. Okay, and we're doing this now for t equals 0. Okay, this is just taking our previous expression, but now having substituted in the expression here for Q in terms of A and A dagger, and similarly for the magnetic field operator. Okay. All right. If there's any questions, just feel free to jump in. All right. So at this point, actually, I want to point something out. So here, what you see is that these expressions here for the electric field and the magnetic field operators, they have still the same spatial component here that we had on the previous page when we didn't do the quantization. What's different is that the amplitude is now replaced by an operator. So the way to think about the quantization, or like how to describe photons, is you solve, in this case, Maxwell's equations, and now then you have all of Maxwell's equations. Okay, the spatial structure of the solution is identical. It's just given by Maxwell's equations. Same, the solutions are the same as before, quantum mechanics was discovered. What's different, what quantum mechanics tells us, is that any solution to Maxwell's equations, which has that spatial dependence, can only have discrete values in its amplitude. Okay, and we see that from the fact that these here are operators, which when you apply it to a certain state, give you some restricted set of amplitudes. So when you measure the amplitude of the field, that is quantized. Okay. So now this was so far.
There's a question in the Q&A.
Okay, good, very good, like that. Let me see if I can. All right. Okay. Question in the Q&A. Oh yeah, okay, here. Okay, the question is, why is Q sub I, and why is the commutator of Q sub I, Q sub J not 0? It depends on the position. Yeah, let's see. Well, Q sub I, and yeah, that is 0 actually. Yeah, so first of all, if I and J are, so the question is, why is the commutator of QI QJ not 0? It is equal to 0. First, let's consider if I is equal to, if I is different from J, then it's 0 as we had before. And if yeah, so and then if QI comma QI is also, it's also equal to 0. Did I have a typo there? Let me see. Oh, I had I think I have a typo. Good spotting. Yeah, this should be, that's my bad. Yeah. Awesome. Okay, I want to thank Jack. You're exactly right. That should have been a 0 here, just like this one was 0 as a typo. I copied that over incorrectly. Thanks a lot. I very much appreciate that. Keep it coming. Okay, there is very likely some other nuggets of errors in there. So slide 8 will be fixed. Thanks a lot, Jack. I appreciate it. Okay, so that was at time equals 0. Now let's see what the system, how we evolve this in time so that we can look at other later times. So one way to do that is to work in the Schrodinger picture. So here we have the time-dependent Schrodinger equation. If the Hamiltonian is time independent, this has a simple solution that we can just integrate. In this case, the state at a later time is just equal to the familiar form of the sum over J of state psi sub J, which is the actually let me change the notation here. State J C sub J. Okay, this is just from our previous page. E to the I omega J T. Where these are the energy eigenvalues, and these are the eigenstates of the optical field, and these are the amplitudes. Now, if we expand this expression, into this expression here for the state J, if we expand that thing into the set of the Fock bases, so this one being then C sub J n times Fock state n, okay, for state J, okay, dot, dot, dot. Now this goes in here, and then when we bring these two sums together, we can write it this way. This is telling you that the overall state of the optical system is the sum over each mode J, each of which is expressed here in terms of a basis of the Fock basis, the number of photons in that mode n. All right, so that's one way to do the state evolution. And the other way is to use a Heisenberg picture, and this is actually going to be more fruitful for us. And here, I'll just show you quickly how that's done. So so here you consider an arbitrary operator that maybe we want to measure. What is the expectation, for example, of some operator that we might want to measure, some operator A, okay? So in the Schrodinger picture, I would have my time-dependent state here, bracketing the operator A to get the expectation of the operator value A. But I can alternatively say that this thing here is actually evolving. This is some initial state psi naught, okay, and it is time evolving by some unitary evolution U. I got to do dagger here because if we write that psi at an arbitrary time t is equal to the unitary evolution operator times the initial state psi naught, okay, plug that in here, and then what we have is this. Okay, on psi naught. And now we see that there is an equivalent way to represent the state evolution, namely by keeping the state fixed. Okay, so let's keep the state fixed as it is originally, and then evolving the operator, okay, according to this transformation here. And so in particular, if we do this, then we can find for general case that there's this equivalent of the Schrodinger picture, this Heisenberg picture, differential equation for the evolution of the operator, which is given by the commutator of the operator with the rotating expression here for the Hamiltonian, and when we apply this to the operators that we are currently talking about, namely the raising and lowering operators, then assuming that you have time independent Hamiltonian, okay, in the case of the cavity, that's the case. Cavity is fixed in time. Then it's easy to integrate this differential equation to produce the time varying expressions for the lowering and the raising operators in the Heisenberg picture. So when we do this additional subscript here, that we're talking about the Heisenberg picture. Okay, and that's equal to the original at time equals 0, raising and lowering operators respectively, multiplied by these phase evolution terms. Okay, so okay. Okay, so that's called the Heisenberg picture, and so now in review, what a lot of people when they do quantum optics fail to appreciate is that that a mode is a solution of just plug and chug, essentially finding the solution to the classical Maxwell's equation under the boundary conditions. That gives you all the modes that describe the solution space. And in our case, absent charges, this would be a solution to solution. Let's call that the outcome here of that. Like that mode is the solution A. Okay. So from this, we can also find the magnetic field, and then this electric field here is then is given by the sum over the spatial distributions here of different modal solutions. This here is the time dependence, and then this is our classical solution to the electric field. And then what quantum mechanics tells us is that it's the mode's excitation and hence its amplitude that's quantized. And since the Hamiltonian for the harmonic oscillator is mathematically identical to a mechanical harmonic oscillator, we quantize it the same way as the mechanical harmonic oscillator was quantized. And that gives us the final form of the operators for the electric and the magnetic field, which is shown down here on the left-hand side. Okay, and so at this point here, I plugged in the time-dependent form of the raising and lowering operators, and this is why now here we have the full thing with not only like at any position r, but also at any time t. Is this is the operator for the electric and the magnetic fields. And this coefficient here, E sub j, now is it comes in from a normalization condition because we want to work with a orthonormal basis set. Okay. Any questions up here? No questions so far. Okay. Now let's consider so now we have solutions that are in this pure state. But what if in general you don't have a pure quantum mechanical state? You might have a mixture because there's some uncertainty, classical uncertainty of your knowledge of the system. To be able to represent that, or to be able to represent subsets of a larger coupled quantum mechanical system, it's useful to introduce this density operator. This density operator here is the sum over the these collapse operators here onto the modal basis of eigens of the states that make up the system, with some probability weighting factor here. This is this gives a classical probability, i.e., the sum of p sub I over all states psi sub I that make up the system is equal to 1. Okay, whereas if this was a quantum amplitude, we would have seen something like an absolute value squared, but this is a classical amplitude. So this here represents our classical estimation probability of how much of the state vector psi sub I is in the system. Okay. Okay, and so this it's important that the density matrix this must form a complete basis, and at that point one can ask like how pure of a state is it? Okay, so for that you can look at this this purity here, which is given by the trace of the density operator squared. This is easy to appreciate by an example. So suppose that you have a pure state. That means that your density operator is equal to, okay, there's, you know exactly which quantum mechanical state it's in. There's no classical uncertainty. That is to say, like P sub, let's say 1 is equal to 1. P sub 1, this is equal to 1. You know exactly what state it's in. It happens to be in state 1. And then you have density up, then you have this projection here, psi. Now that's your density operator in this case. Since all the other P's are 0, we just drop them. Okay, so this is your density operator. Now let's see, what does the purity evaluate to in this case? Well, it's equal, so by this equation here, it's equal to the trace of the density operator squared. Okay, so this is psi on psi. Let's just see what, let's see. Yeah, the operator squared would be this squared and this thing squared. Okay, well, this is equal to psi on psi because we're talking about normal orthonormal basis. Well, because this here is equal to 1, and so so the trace then yeah, so then the trace here is equal to 1, and so the purity here has to be between 1 and 1 over d, where if you have a fully mixed state, that is like if you're working in a d-dimensional, if you're working in a d-dimensional density matrix, so you have like d contributions in your, you have d, the psi is in a d-dimensional space, and you have no knowledge at all of what density, what is the distribution that constitutes your quantum state. Then you can plug in here 1 over d, and you can convince yourself that then in that case the purity evaluates to 1 over d. So yeah, and moreover, it's useful often to look at the fidelity of a state rho with so if you have a state rho of your system and you wanted to produce the state sigma, then you can also look at, so then you can take this expression here that gives you the how close, what is the overlap between the target state and the actual state of your system. Okay. All right, so now we're getting into photonics here finally. Just want to check the time. Yep. Okay, so now let's talk about single qubit gates of optical fields. Okay, so we have quantized the optical fields. We know how to describe a single mode, and we now also know how to describe two modes. Let's in particular say that there exist two modes here. Let's say these are modes A1 and A2. Okay, and we know how to deal with each of these modes, A1 or A2 separately. Okay, at that point, you could say, okay, let's see if we can encode some quantum information in this. Let's put let's define a basis, a logical basis to encode this quantum information. And we can choose that different ways. Like you could, for example, you could really do anything you want. You just need to have two states that are that can encode your logic levels that are orthogonal from one another. But what people often do is you consider a dual rail representation where there's a single photon either in one mode or in the second mode. And you might call this one here a logical qubit. The logical qubit is 0, and this here is the logical qubit 1. So this input state here, for example, would be the logical qubit 1. Okay, so that's your qubit encoding, your logical qubit encoding. And then, like, what if you want to do a gate on this, right? So suppose you want to do like a rotation on this qubit. All right, so in optics, we can do this using some sort of programmable interferometer, and perhaps the sort of more common way to do that is to use a Mach-Zehnder interferometer, which is illustrated here. This Mach-Zehnder interferometer consists of two beam splitters that we'll talk about in a second, and phase shifters. Okay, at least two independent degrees of freedom on the phase. Here I see this, I've distributed them equally because of reasons of that we'll get into when we talk about the photonic circuits. It's basically loss balancing. And then there is some external phase shift here. Okay, so if we wanted, for example, to realize this transformation here, we can, okay, we want to apply this particular gate here, okay? Now we can realize this gate using a Mach-Zehnder interferometer. Why? Because if we look at the Mach-Zehnder interferometer description of this thing here, okay, it's equal to, okay, we have an input, all right? So here would be the input state. If we were to use this, okay, this here is mode A1 in the top row and mode A2 in the bottom row, okay? This could be, again, this could be representing your optical field strengths in there. All right, now these guys encounter a beam splitter. This is, in this case, we're assuming that this is a, yeah, so this is a bulk mode beam splitter that has this form. And we can, this, like, if I don't want to derive this separately, but for a free space beam splitter, the expression you can derive is given by this equation, whereas for a directional coupler, it's typically denoted in this way. You see there's a slight difference in the notation, but their function is essentially the same. Okay, so if we start with this field here, then we can transform that through this first 50-50 beam splitter, which we can obtain using the free space beam splitter, plugging in theta is equal to pi over 2. That gives you this expression here. And then it passes through this segment here, which is this propagation through phase shifters in the top arm and in the bottom arm. Okay, and then the system encounters a second beam splitter, which is here. Okay, includes the 1 over square root of 2. And then finally, the field encounters a phase shift that's only on the upper rail. So you see it's only applied here to the upper rail, not to the lower rail. Okay, and when we multiply all that stuff through, we get this expression, which gives us sufficient degrees of freedom to do an arbitrary rotation around the Bloch sphere of this qubit that's encoded in this case in this dual rail basis. All right. Any questions up to here? Okay, so now we have a waveguide. We know how to quantize the optical field on the waveguide, and we know how to transform the fields of that waveguide through a directional coupler, phase shifter, and a combination of them to produce this arbitrary single qubit gate on the optical logical qubit. So at this point, I think we should, like that's essentially what it did, what I wanted to get to, insofar as how does the quantization actually work of the optical field, and how does that set us up for tracking quantum optical fields on photonic circuits and so on. So just let's do a review here. I don't know how that's going to work over the, over the Zoom, but we can. I think I'll see how it goes. I will just ask you, and maybe somebody can volunteer. Otherwise, I'll just talk us through it. Okay, so question 1, for example, could be from the classical Hermitian operator that describes the Hamiltonian, namely the energy of the system here, and using these expressions here, these normalization expressions for the momentum and position operators, derive this operator that I had just given earlier in the that I just put earlier in the notes. So how do we go about that? This is probably difficult to do over Zoom, but all right. So what we do is we remember that the Hamiltonian was equal to 1/2 times the sum over j of p sub j squared plus q sub j squared. And then we can substitute in these operators here. And from our earlier slide on the equivalence of the harmonic oscillator for the mechanical system and the harmonic oscillator for the electromagnetic system, relate P and Q to A and A dagger, and then using in addition the commutator relations, that's how you derive this expression. Okay, this one, that's a bit tedious. It's difficult to do here on Zoom, but this one here is probably more fun. It's easier to do. Describe the vacuum fluctuations of the electric field in the electromagnetic mode. Okay, so vacuum fluctuations. So that means that all n sub j, all the fields j are in the vacuum. So n sub j is equal to 0 for all j in our expression for the electric field. Okay, so we want to know the fluctuations in the electric field. All right, so this is the electric field. So we have the electric field operator at position r and time t. Now remember, we have that guy from earlier from the slides. So we want to assign what are the fluctuations. Okay, so for any like quantity that we sample, let's say quantity A, which is described quantum mechanically by an operator A, the fluctuations would be given by the this expression. So the expectation of the operator value minus its mean squared. Sorry, and write so well here, squared. Okay, and then this is the expectation over your state, which in this case, we're assuming to be the vacuum field. Okay. So for this, we should, okay, so for this, we can because we have the commutator relations that A sub j and A sub I are equal to 0 if we evaluate this term here, all cross terms will go to 0, and that this here instead is equal to the sum over the vacuum fluctuations from each mode separately, j. So this here is the mode j, psi sub j, on this fluctuation, and then it's summed over all j. So we just have to worry about one of the modes. So let's say we take one of the modes, like, one of the j's, and then it's in the vacuum, and we're looking at what is the fluctuation of mode j of now this operator here. Okay, so a minus. So by the way, it might be useful for you to do this on a piece of paper. I find that I really learn best if the teacher does something on the board, but really just by writing, it's quite helpful. So you should really take the opportunity to just write this out yourself and see what you get. Maybe you find Jake earlier that find an error in my notes. Best to write along. Okay. Now this thing here is equal to 0 on a squared minus 2a. This is from the expectation here. All right, let me fix this. Okay, so this here is equal to all right, so if you think you distribute the square here, then you get a squared, and you find what is the expectation of a squared, minus you have the expectation of a times the expectation of a, which is this here is a real valued scalar number. So you get this expression here. Okay, and then you find ultimately plus the expectation of a operator squared. That's that term. Okay, so so here this is, and all of this stuff here then becomes a squared minus a expectation squared. Okay, that's the quantity we want to find, where a is equal to this electric field E. Okay, so all right, so now remember that the electric field operator, okay, is equal to some stuff for a single mode field, because we're just looking at one particular j at the moment, that has a sub, so we can drop the index for now. A has the expression a plus a dagger, okay, times some complex number psi. All right, which also has the position in it. Okay, so now the a, since this has, if you apply a on the vacuum field is equal to 0, then the expectation of a is 0, and similarly we can find that for a dagger the expectation is 0. Okay, so this term here goes to 0, but we have to still find this term, and that term has a surprising outcome. Let me just clear the page here. Okay, so now we are looking at what is the electric field operator squared expectation. Okay, that's the last term we have to find in that problem here. Okay, so this here is equal to C squared E sub j. Is it E sub j? E sub j squared And then we're looking at the expectation of A sub j 0 times e to the minus I omega t plus a sub j dagger e to the I omega t squared. Okay, and here, if you now if you write this out, all terms a squared or a dagger squared will drop out to 0, and what you're left with is, as a term that is here, the term that goes a times a dagger plus a dagger a, okay, on 0 on the vacuum field. Okay, so what is that? All right, so we know how to, well, if a is applied to the vacuum, then that term drops out. So now the only thing we have to check is what is the term, the only thing that's non-zero is the term a dagger on the vacuum state. And now we can bring in our trusty commutator relations, namely that a dagger for the same mode is equal to 1. And so, so this guy here is the expectation of 0 on 1 plus a dagger a on 0. That term again drops out to 0, and you have a non-zero term left over. Okay, which basically which has this the position information. This is what I previously said is psi term in it. Okay, it has position psi squared term in it. So the variance depends on the position of the probe that you stick in there in this cavity, and whenever the sign value, sign of k sub j times z is equal to 0, then the variance of the electric field also goes to 0. It's not surprising because the electric field itself is 0, so there would be no vacuum fluctuations at that position in the cavity mode if the electric field itself is 0. But in the location where you have like an antinode in an electric field, where, for example, the sign is equal to 1, there you have a strong vacuum fluctuation, even that you have a non-zero vacuum fluctuation, even if the number of photons in that mode is equal to 0. Okay, and that's important. Gives rise, for example, to spontaneous emission enhancement and all kinds of things that we use photonic circuits with atoms for. It allows us to tailor the light-matter interaction by making use of this like non-vanishing vacuum fluctuation. And moreover, this, if you look back at the notes, this prefactor that we said here is going to be like the vacuum fluctuations variance is equal to that factor squared. That prefactor, that e sub j squared prefactor, it has a value. If you go back a couple of slides, h bar omega divided, so omega sub j divided by v times epsilon naught. Okay, so squared. So that's the vacuum fluctuation here, the variance of the electric field is equal to this factor here, which depends on two crucial things. Okay, so first of all, the larger the frequency of the mode that we're looking at, the larger the vacuum fluctuations. Okay, the variant or the standard deviation of the electric field, if you're measuring it in time, standard deviation is proportional to the frequency of the cavity mode, and it's inversely proportional to the mode volume of the cavity. This mode volume, incidentally, is not like if you try to make this mode volume the smallest that it can be like without using some, let's say if you're in a homogeneous medium, without using some like methods like we introduced in my group for electric field concentration, then this cavity mode here has a minimum mode volume of the order of lambda cubed. And then you can see that this whole thing here scales as this basically that the electric field here, that this here goes as lambda cubed, which is proportional to 1 over omega cubed, that the vacuum fluctuations altogether have a very strong dependence on the wavelength of the field. But I guess the most important thing is that that even when the field is in vacuum, that the fluctuations don't go to 0, and it's that fluctuation that gives rise, for example, to the spontaneous emission decay of an atom. All right, and so that would be the second exercise here, and the third one would be consider 2 identical photons incident on ports 1 and 2 of a beam splitter, and describe the outgoing state. So let's see if we can do that one. And maybe, let me think if there's I don't see an easy way to do this interactively at this point. So how do we do this? So like what we're saying is there's one field, A1, there's a second field, A2. They're incident on a beam splitter, okay? So we have the 2 fields, A1, A2, incident on a beam splitter. Okay, let's say that how do we write the fields? Okay, so let's see, how do we write the initial state of a two optical mode system? Okay, so here's mode, actually I want to write it like this. Here's mode 1, here's mode 2. And let's say that initially they're in the vacuum. Okay, so the number of photons in both is equal to 0. So let me write it this one. And the notation here is that in mode 1, there's 0 photons, and in mode 2, there's 0 photons. These are the 2 modes, let's say 2 optical beams. Okay, and we have, what we're doing is we have so now we want to put 2 photons, identical photons, into ports 1 and port 2. Okay, so how do we do this? All right, well, we start with a vacuum state and we apply the raising operator, A1 dagger, to put 1 photon into mode 1, and we apply A2 dagger to put 1 photon into mode 2. Okay, now these fields here will go through the beam splitter, and what we want to find is what is the outcoming state here? Okay, what is that equal to? And now you see why actually the Heisenberg picture is oftentimes very useful to describe the fields, because like the state here is simply given by the evolution of these Heisenberg operators, the field operators. And we know that evolution because that's transformed through the beam splitter matrix that we've already had before. So that one, so for example, if we do have the bulk beam splitter, then if you go back to that, like that transformation was given by this unitary for the beam splitter in free space is equal to this expression. And now we can say, okay, what are the output fields? Let's call these output fields here B. So the output operators are B. So B1 and B2 are equal to the unitary here times the input fields A1 and A2. And I know I'm doing this for the lowering operators, but the same applies to I can just do mission conjugate. Okay, since this is unitary. Okay, and so what is the output state here? Okay, so this is equal to A1 dagger plus A2 dagger, and below we have A 1 dagger minus A2 dagger. That's equal to that. There's a 1 over square root of 2 from the u that comes over. Okay. And so now we can solve for, let's solve for A1 and A2 in terms of B1 and B2. Okay, just inverting that matrix equation gives you A1 dagger is equal to 1 over square root of 2 times B1 dagger plus B1. And A2 dagger is this, like the same thing with a minus sign. Okay, so now our state, psi, our initial state, okay, has now rewritten it, psi, the initial state here, that one is A1 times A2 dagger dagger on the vacuum. Okay, so the output state here is 1 over 2. Now I'm doing A1 and A2. I'm re-expressing it in terms of B's. Okay, B1 dagger plus B1. Sorry, it should have been B2. B2 dagger times B1 dagger minus B2 dagger times the vacuum is B1 dagger squared. All right. B1 dagger squared minus B1, B2. Remember that they commute. So that cancels the term B2 dagger B1 dagger. They cancel because B1 and B2 commute. And then we have minus B2 dagger squared. B2 dagger squared. Oops. Okay, so our output state is this on the vacuum. Okay, so this is our Hong-Ou-Mandel effect. Why? Because it shows us that the system either has 2 excitations in output mode B1, or it has 2 excitations in output mode B2, right? But it doesn't have, there's no way that the output mode, if you were to measure it, has 1 excitation or 1 photon in B1 and 1 excitation in 2. Those terms cancel, and that gives us the so-called Hong-Ou-Mandel effect, right? So the photon bunching. Okay, and this kind of approach here is particularly easy to write when you do this Heisenberg picture by keeping track of the operators. You can do it also in the Schrodinger picture, but there it's very tedious because you have to transform the quantum mechanical states, and you have to make sure that they are properly that they have the right symmetry relations, namely, because they're 2 identical photons, you should be able to have the same outcome if you swap the order of them. So you have to symmetrize the input state, and that makes it quite tedious. But if you do it this way, in the Heisenberg picture, it is, just 2 lines of math, and you have your Hong-Ou-Mandel effect. Okay. All right. So any questions up to here? Okay, like I said, this was the difficult part, but I thought it was important to go through this. But let's think again about this this Hong-Ou-Mandel effect here, right? So what we just left with in this exercise. It's really that bunching that makes it so difficult to predict the distribution that you would get in photon resolved sampling from many optical modes, like in this large interferometer. That is at the heart of this boson sampling difficulty. And so you basically like use that weird effect of this photon bunching in this many mode interferometer, and that's really at the core of why this approach here of doing boson sampling has so far held up to scrutiny in claiming a quantum computational supremacy. And then again, like the other problem here is actually rather similar in the superconducting case. It's also a sampling problem. But it's interesting to think about, like, okay, how many photons would we need to do an experiment that would show some sort of a quantum computational advantage? And the way to think about that is that, like, we just had an example here in the previous slide where we have two modes coming in, modes 1 and modes 2, and then on the output we had some so we have some combination of the photon, the optical of the excitations of the optical fields, and that combination it turns out like it's hard to calculate classically, and provided that the output can be in many can spans a very large Hilbert space. Okay, so basically, what's important is what is the size of the Hilbert space that the output needs to be described within, and if that size is large and it grows exponentially large with the number of identical particles that you have going into this kind of a system, if that size becomes large, then your classical computer can't track it. It can't track that contribution to the overall state of the system. And that's really why these sort of like intermediate scale quantum computers have reached this quantum computational advantage. And they can do that if this number of states is very large. Okay, the number of states that you need to describe the correlations of your measurement, if that number is large, then you're in the regime of quantum computational advantage. So how large does n have to be? How large does the number of photons have to be for this 2 to the n to be sort of intractable for classical computers? And so you can kind of like, you can just estimate, like, where does this number come, like, why did it become so difficult in the Google case, or in this case here of the Genway Pan group, at this number of like 50 or 70 or so photons? Why was it at that point that it became so difficult? Well, because at that point, it becomes difficult to track the state if the state is sufficiently coherent. Okay, so like in a supercomputer, maybe you have something like 10 to the like your RAM on the supercomputer might be of the order of some terabytes. Okay, so let's just say it's very aggressive, and you're like, maybe you have 10 to the 15 bytes that you can store in your working memory on your computer. So 10 to the 15 bytes. How many states would like if this here is equal to the number of states, solving for n, okay, so log base 2 of 10 to the 15, you'll see that n is somewhere around the order of 50 to 70 or something like this. Okay, so if you have a better computer, and IBM found, like, they challenged Google's claim to supremacy just shortly after. It's actually an interesting back and forth there between the research teams back in 2019. They said, oh, wait, we can be faster than the algorithm, the classical algorithm that you claimed in your paper. Why? Because they just represented the state in a very large storage computer, a computer with very large storage. And so they got maybe 10 to the 16 or something like this bytes in which they could store. But you see, it's all logarithmic. So there's like rounding error really in the number of particles that you need to get into this quantum advantage regime. So in particular, this one is maybe still the strongest claim, one of the strongest claims for quantum computational advantage. And they say that by obtaining up to 76 photon coincidence, yielding a state dimension of about, oh, this is a type, this is 10 to the 30, they claim a sampling rate that's about 10 to the 14 times faster than using state-of-the-art classical simulation strategies in supercomputers. Okay, so maybe your computer is 10 times faster. That's only like changing that from 10 to the 14 to 10 to the 13. So that's a pretty strong claim, and it's made possible by this interference of the excitations of the optical fields that we had on the previous stage. Basically, Hong-Ou-Mandel and beam splitters taken to many modes gives you this effect. Okay. All right, any questions up to here? Now, why we're interested in it for these programmable photonic systems is that if you look at that paper here, if you look at this paper, all of the optics here are bulk optics. So if this thing had a utility, and there are some proposed applications of this kind of boson sampling machine, for example, in predicting the molecular spectroscopy, vibrational spectroscopy in molecules, if there is an application that's found, then this wouldn't be a suitable device to exploit it, because this thing consists of a bunch of mechanically assembled wave plates. So it would be nice if we had a way of doing this in a programmable, this optical circuit in a programmable way. And that's one of the motivations for the field to go towards programmable optical circuits, but certainly not the exclusive one. Okay, so at this point, I think I want to have maybe take some moment for questions, maybe get a drink or something. And next up, what we're going to do is an interactive notebook, because this has been a lot of me talking to you. I want to have something a bit more interactive. This is why I stayed up until very late this morning to get this notebook prepared for you. And so yeah, so looking forward to doing that. So, but before we get into the notebook, are there any questions? Oh, there's a question. Yeah. Oh, yeah. So Jack again said the eigenvalues. Yeah. N sub j being, yeah. Oh, you asked already half an hour ago. Sorry, I missed that. So N sub j being the photon numbers of the of mode J. Yeah, so those are the eigenvalues of the photon number operator. I don't know if other people see the question. The question was, are the N sub j's the eigenvalues? So yes, they are the eigenvalues of the photon number operators A dagger A on J. All right, good. So let's keep going then. So next up, now we're gonna get try out this thing. This is some Jupyter notebook that I put together, and it's the first attempt here. Many thanks to CJ for putting this into Binder, so it should be available to everybody, and see how it works for me. So you could go ahead and click on it. Oh, I think I should probably share just my whole desktop here. Okay, so what we're doing is, oh yeah, so CJ shared this link, I believe, so I can also share it in addition. Chat here. Oh yeah, CJ says the initial load will take a while. Okay. There it is. Okay, so all right, so now that we know how to quantize these fields, and we can do that for a single mode, and we see hopefully the motivation why it would be useful to go to many more modes. Let's actually get into the physics of the modes. How do we, like, the modes are not as simple as the cavity that we had at the very beginning. How do we solve modes for a more general tool set? And so this here is a Jupyter notebook-based exercise on dielectric waveguides. Okay, I'll just walk you through it. You should have access to it yourself and play around with it yourself. I think in the interest of time, I won't take too long here, but we'll get to take a look at how we can actually, like, what is the internal machinery that we need to be able to describe the modes of a more complicated system like a photonic integrated circuit, right? Okay, so here's one way to go about this. So we're going to look at the modes of dielectric waveguides, like in silicon photonics. All right, so we're importing a bunch of libraries into Python, and then this script here was automatically created by Binder, I think, right? All right, so what we want to do is solve for the optical modes within a dielectric waveguide. And the dielectric waveguide, okay, what is it defined to be? Well, let's say it's defined by the spatially dependent permittivity epsilon. So this is the epsilon naught times the dielectric refractive index squared. Okay, that's the spatially dependent permittivity. So that's that permittivity defines a ridge, let's say, of dimensions width W. We're talking about a waveguide here. I didn't have the time to draw this very beautifully in the Jupyter notebook, as I'm still, and I spent a lot of time on other stuff. So this here is what we're talking about is a waveguide of width W, height H, and some. Okay, so in our problem statement for solving the modes, we have to define everything that we need. Okay, so it has some length, and the length here is specified to be some length L sub Z. Okay, so here you have it. All right, and right, Maxwell's equations requires us to solve the modes. We need to solve Maxwell's equations, and that requires also boundary conditions. So I'm assuming here that we have boundary conditions given by some bounding box, okay, of the transverse dimension L sub Y, L sub X, and longitudinal dimension also L sub Z. Okay, the boundary conditions are that the electric field vanishes in the transverse dimension. So on this edge here, the electric field vanishes. And that we have periodic boundary condition in the Z dimension. So that is to say that the electric field here at the opposite end of the bounding box is equal to some e to the I phi times the electric field incident here. Okay, why? Because when you take the absolute value squared of that, it gives you the same measurable intensity. And so if the field here is equal to the field here times some phase factor, that's guaranteed, that condition is satisfied. All right, so that's the setup. Okay, and so, all right, so what we need, all right, so the problem statement is that. Now the approach is, so what we need to do is solve Maxwell's equations in this volume for the electric field E. Okay, if we have E, we can get magnetic field H from Maxwell's equations. So if we consider the problem in a volume of these dimensions, L sub X is much greater. So like this box that we're putting around it, and that's the box that we require that the bounding box around our problem is such that Lx is much greater than W, so that we can, so there's no evanescent field at that boundary. So in that way, we assume the boundary conditions, as we just said. And then what we have to do is apply Maxwell's equations, which I've written for you here. Okay, just as a reminder. All right, so what is in here, right? It's got some charge density rho, or on the boundary sigma perhaps, and it also has some currents that are volumetric currents or perhaps surface currents, and that's defined down here. But we make an assumption that the material is isotropic, so the material properties like the permittivity and permeability are independent of the direction of the electric field or magnetic field. That's what isotropic medium, dielectric medium means. So when I say that the material properties like permittivity and permeability do not depend on the direction of the electric field or the magnetic field. So that's not normally true, but we're going to assume it here. It's not true for many crystals, but we'll assume it here. It just makes the math easier, but it's easy to deal with it if you do have a non-isotropic material. Okay, but mathematically, what that means is let me see here. Yeah, I just take this. I think that is okay, let me see what happened here. Oh, do I have to recompile this? All right. Let me just reload it. Okay, the material should be linear, so that if we look at the displacement field or the magnetic flux density for this, when we have a sum of electric fields locally, then that is distributive. The material should be non-dispersive, meaning that the material properties are independent of the frequency of the field. This also doesn't necessarily have to be true, but it makes the math easier for now. It's provided that the dispersion is relatively small, then this is you can still use the same exact treatment as before, as we're doing here, and the material is non-magnetic. That is to say, the material has a magnetic permeability that is the same as the permeability of free space. So there's no material, the material is not magnetically active and it doesn't produce its own magnetic field. And finally, let's assume that there are no free moving charges and that the space charge density, which I forgot to include here, is also equal to 0. Okay, under these assumptions, then we can take the Fourier transform of the field, take the temporal Fourier transform, and that turns all of the time derivatives of Max's equations, these partial derivatives with respect to time, and allows us to evaluate these, because each of these fields here is equal to some b initial times e to the I omega t, and then this here just brings out the I omega. That's why we see here, or j, this is here we're writing out j notation, j omega times mu naught here. Okay, so and if it's time invariant, moreover, we can approach the problem by just decomposing it into this. So like we're decomposing into Fourier components, and this allows us to take the Fourier transform of Max's equations, which is given here. And then we're also, let's consider like the field at one particular frequency, omega, and in the absence of sources and of charges and currents, we can then simplify Max's equations to this form here. Sorry, there's again I fixed this before the Jupyter notebook is released to everybody or updated to everybody. There should be more obviously a space in between. So this here is d equals epsilon e, which is equal to epsilon n squared, epsilon n squared. This is the relative permittivity here, n squared times e, and space b is equal to mu naught h, because we're in because it's just the we're dealing with the permeability of free space for the magnetic component. All right, then we apply Maxwell equation boundary conditions, which I'm plotting down here again, reproducing here, and so that sets up the boundary conditions that we have on the field, on the dielectric constant. So now we can look at the at a simple case of this problem, namely longitudinally invariant waveguides, and that is the case because we're considering a periodic boundary condition. That means that an eigenmode propagating the z direction can be represented in this way, where where the periodic boundary condition means that E after some distance LZ plus R is equal to E naught X, Y, E to the j beta times LZ is the boundary condition for the problem up there, with beta being the propagation constant of the waveguide. So now the eigenmodes in an arbitrary shape rectangular in a rectangular waveguide are not analytically solvable, but they can be approximated analytically by solving for modes in a structure that's invariant along both the propagation direction and the perpendicular directions. So here I provide you more detail. Oh, thank you, CJ. You put in, I think, this click to expand for more detail, perhaps. So here here's the full math on that part. And now let me just get to how we can actually represent this and mathematically solve it in Python. So let's say so first of all, let's just see if we could take a moment. Oh, so somehow this does not work. Oh, I think I know what. Never mind. All right. So now let's so in this quiz here, we can say which of the following modes propagates in a dielectric waveguide with a rectangular cross-section? TE modes, TM modes, both TE and TM. I will certainly see both TE and I would encourage you just to take, let's say we take here until 5 minutes to the hour, 1.5 hours through in that point, 5 minutes to the hour for everybody to just go through the problem here, problem 0, and if you have time, you can already go into problem 1, which solves for the TM and TE modes in a slab waveguide. Okay, so we're going to take about 5 minutes. So I have my timer, so we'll resume in 5 minutes to the hour. Okay, so we're going to continue here. And so like I said, this is a completely new Jupyter notebook. I realized I see already here a mistake in my problem statement. This should have been which of the following modes propagates in a dielectric waveguide with a square cross-section? And then the answer would be C. But for the rectangular cross-section, if I had made some more clarification that it's single mode and that the rectangular cross-section is such that the W is greater than the H, then the answer was what I previously had written the question for, which was A. Okay, so apologies for the first one. Ignore the first question. The other ones are right. What is the relationship between the refractive indices of the core and cladding of a waveguide or a step index fiber equivalently? So in the that is, of course, the refractive index of the core has to be greater than the refractive index of the cladding for total internal reflection confinement. Question 3 is, what is the purpose of the cladding layer in an optical fiber? Here it's the cladding layer is used to reflect the light back into the core. In the case of the waveguide, the lower refractive index material surrounding the waveguide keeps the light, reflects it back into the core. Maybe people might have, I think a legit answer here also would have been the cladding can also protect the fiber from damage, but it's really primarily for index guiding. And question 4 is, how do TE and TM modes differ in their electric field distribution? Okay, so for the TE mode, and we'll look at that now in a second, verify it mathematically, the TE modes have, the answer is B here. The TE modes have an electric field that's completely transverse to the direction of propagation with a non-zero transverse magnetic field. Okay, and the TM modes have a magnetic field that's completely transverse to the propagation direction with a non-zero transverse electric field. So that would have been B. Any questions on that quiz? Okay, so then we may be well prepared for getting into the next problem here. This is looking at the TE and TM mode solutions in a slab waveguide. And here I should point that I built this on top of some earlier homework exercise that Dr. Carlos Arando Ranz, a postdoc in my group, had contributed to a class that I had previously taught. So, so what we see here is what we want to do is we want to find what is the mode shape of the TE and the TM modes, given the refractive indices of the core and the claddings, the wavelength and the slab thickness H and the width. In this case, width D, width W and D are used interchangeably, the same. And we assume here one other thing. We assume that the pulse length that we're sending in an optical pulse that fits within the bounding box of the problem that we have here, that like the whole pulse in its full width at half maximum fits within a length LZ given by the speed of light in the medium divided by 1 over the bandwidth of the pulse. Okay, so the way that I'm approaching this here is, so we first define the we define the function slab here, which has inputs of the physical constants, okay, the wavelength, the dimension, the width of the waveguide, which again D is equal to W here. So D here is in units of microns, and then we have to calculate the wave vector value. K naught is equal to 2 pi divided by the wavelength, the frequency K naught times the speed of light C, and then the beta, the propagation constant, here is solved for in this problem, in this notebook. Okay, so what we're doing is when you go through the background on, for example, here, in this, you can see the background for this, for finding the solution from this online solver here, Computational Photonics, or from your textbook. Yarif is a pretty good textbook for that. Amnon Yarif's book on quantum electronics. What you have to do is you have to solve these really nasty transcendental equations that requires a nonlinear equation solver. But you can do this in Python and then solve it, and then you can go through and plot it. And this is what the rest of this thing here does. I'm plotting in figure 1 the electric field and the magnetic field in the different in its different components. Okay, here also calculated how many modes actually exist in this waveguide given the dimensions of it, and that's what it spits out as well. Okay, so to cut a long story short, let's take a look at the solutions here. So here is the solution, and what you see here is the electric field of, let me see, so there's 2 modes here. Let's start with 1 mode to begin with. Oh, this is slow in the binder. Okay. Okay. Yeah, so this should work. So, all right. So here, if the cladding is at an refractive index of 2, and the cladding on top is air, and the cladding on the bottom is air, and the wavelength is 1.2 microns, and the width of the waveguide is 1 micron, then we can plot, let's say, the TM mode. And there exists a total of 3 modes. So this is why at any point here, you will see there's actually 1, 2, 3 values for the electric field in the X, Y, and Z directions, and similarly for the magnetic fields. Let's make it simpler. Let's just go to 1 mode. So like, what can we change here to make this single mode rather than triple mode? Okay, well, so one thing is we could, for example, make the width of the waveguide smaller. Let's see. Okay, there we go. The number of modes that are solved is now 2. Now that I'm at 1.2 microns in wavelength, and the width is the width of the slab is half of a micron. What else I could do? I could like lower the core refractive index. Okay, so here we see, okay, now we have exactly one mode. Now it's single mode. Alternatively, what I could have done is I could raise the cladding refractive index to make it single mode, presumably. So let's just surround the material with silicon dioxide. Okay, and so here we go, for example, like, so if we have a refractive index of 1.7 surrounded by a refractive index of 1.5 at a wavelength of 1.2 micron with a width of 500 nanometers, we have one mode for the TM mode. What about the TE mode? Okay, there's one mode as well, and we can see the, so here we can see the electric field has, okay, the absolute value of the electric field is maximum for EY in the TE mode, and for the TM mode, this should have been, my bad, this should have been H, sorry, I see, yeah, this should have been HX, HY, and EZ. So for the TM mode, the magnetic field component is maximum. And whereas for the electric field component in the waveguide is maximum. Okay, so I'll fix that. Let me make a note here. A lot of programming to get this to work, but I'll send out an updated version of that to you. So. And down here, it gives you also the effective refractive index, which is which gives you the propagation constant. So it's your the two are you can calculate one from the other. Okay. So there we have the mode components. Any questions about this? Okay, the point of this is really to have an interactive tool so that you can check for yourself what the modal solutions are. Again, this is solving Maxwell's equations, and then the quantum mechanics comes in that it sets the amplitude of the excitation of these modal solutions. So like, for example, here I've actually, so that's why actually here in the electric field, I express it in terms of units of this normalization factor. So here, the units here are, h bar pi, or h over 2, if you will, times the bandwidth of the pulse. So the electric field here is in units of square root of essentially the bandwidth of the pulse divided by the width times the wavelength. So if you have a single photon exciting that segment of a waveguide, this normalization factor allows you to convert that single photon excitation of the waveguide into what is the electric field in terms of volts per meter. And so, for instance, this here is for the vacuum. This would be the vacuum field. And then to get what the electric field would be for n, like an n photon field. What is the or what, like for a coherent state with a mean photon number alpha squared, the electric field of the vacuum would be multiplied by alpha. And here what we see is that this prefactor depends on the mode, the pulse width. Okay, what is the pulse bandwidth of the field that we're looking at? And so, in other words, the larger this omega, this pulse bandwidth is, the shorter the optical pulse. And we're saying that our bounding box bounds the optical pulse. So that's one mode in the waveguide. And the larger you make the pulse, the larger the vacuum field, and that's also the larger the field is if you have it excited by some number of photons. And so like obviously an ultra short pulse should produce a much stronger electric field, even if it's excited with 10 photons, than a long stretched out pulse that's excited by 100 photons, for example. And then what else is here? So this, and the electric field is inversely proportional to the square root of the area, the waveguide cross-sectional area, W times H, or D times H. Again, W and D here in my notes so far are equivalent, and inversely proportional to the square root of the wavelength. So if we want to have a strong electric field given some number of photons exciting this system, you should make the wavelength small, you should make the bandwidth of the pulse large, and you should make the cross-sectional area of the waveguide small. That's why it's better to do like nonlinear optics with waveguides than it is with like ridge waveguides, for example, than it is with fiber, right? Because your cross-sectional area is like 100 times or so smaller than in a fiber. And there's a question. Okay, cool. How to enter pending input. Okay, CJ is on the job. Thank you, CJ. Okay, so any questions on this? Hopefully this will be some useful, valuable resource for people as well to have this. Okay. Okay, good. All right. So that's how we, all right. So now just like, let's recap where we have gone, how far we are so far. Okay. So where we are thus far is, so now we have quantized the electromagnetic field. We've shown how to quantize an arbitrary number of modes on a in an abstract fashion, and now we've looked at the physics of solving what the modes actually are concretely on our photonic integrated circuit. Okay, so that's where I wanted to get to. Now we have all these tools, and now we can start to see what we can do in putting them together. Okay. All right, so now we're going to get into some more practical considerations. So we had this waveguide calculator, and with that waveguide calculator, you can should be able to reproduce the results that are shown here. So, so for example, if we want to make a single mode waveguide, we want to make sure for, let's say, for the TE mode, you can go to the simulator and say, okay, suppose you start with silicon. Let's just do it. Okay, why not do it? I haven't tested this before, but it better work out. Okay, I always assumed that is about right. Well, we calculate this stuff using finite difference time domain simulations, but this is a semi-analytical approach that actually works well and is instantaneous. It's actually really nice, I think. So what if we wanted to do the silicon photonics? Okay, so silicon photonics has a core index of 3.5. That's the refractive index of silicon at about in the infrared, in the like at 1.5 micron, let's say, in telecommunications wavelength. And the cladding on top and the bottom is 1.5, which is the refractive index of silica, approximately. And let's work here at a wavelength of 1.5 microns, 55 microns, so 1.6. And we want to be, okay, so now that what is the question is, what is the maximum width that I can have to ensure that it's in the single mode operation? Well, sometimes you want to, it's useful to have multi-mode operation in a waveguide, so more than one TE waveguided mode, but you have to be very careful because your the two fields can couple in a way that you don't know in advance, because it's difficult to fabricate something exactly to nanometer precision to your specification. So you generally wouldn't know what the coupling rate is between these modes and what the dispersion is between the modes. So that's generally a way, generally people want to work in a single mode configuration. Okay, so if we made the waveguide width 500 nanometers and we excited the waveguide with a mode of TE polarization, then we would have two modes. No good. All right, so what do? Well, we can't change the cladding and stuff like this. That's difficult to change. The wavelength is fixed. Somebody wants to work at 1.5 micron. What we can do is reduce the width of the waveguide. Okay, so at 400 nanometers is still multi-mode. Okay, so here, so between 200 and 300 nanometers for the thickness of this waveguide, which is in the code, you want to have a width of about 200 nanometers. I think the thickness should be about 300 nanometers. And that gives you a single mode operation for the silicon waveguide. Actually, let me just check. Hold on. Let me just check that I had rerun this again properly. Yeah, that's right. N is 3.5. Should be able to do this yourself as well. Let me know if you find something weird. 1.55 wavelength. Yeah, so at about 200 nanometers to 300 nanometers, we have a single mode waveguide. Okay, all right. So let's go back to here. Okay. All right, so that's our waveguide. Now we assumed in that example that we had a straight waveguide with sort of like a longitudinally symmetric problem. But if you bend the waveguide slowly, then that solution just in a curved space is a good approximation. If you bend the waveguide fast, then that solution does not work, because you can, like in the turn, you can get a multimodal behavior that can cause you a deviation of that mode propagator that I've shared with you, and the actual system. So generally, generally people actually bend the waveguide mode gently to avoid any sort of higher order excitations. Or if you do have a large enough waveguide that is multimode, you try to stay in the fundamental mode by an adiabatic turn, okay, so that you remain in the fundamental mode. So that means a very slow turn. Or in this case, you want to have a slow convergence of these two waveguides in this directional coupler, because if these like modes came too quickly, then you would not stay in the adiabatic limit, and you might excite some higher order modes of this two mode coupling structure. Okay, so we're looking here at a silicon on insulator photonic integrated circuits. We have bends, we have directional couplers, we have our, like, this is how we do our unitary transformations, right, on the single qubit, for example, basis. But there's imperfections. For example, they have a surface roughness that can cause losses. You might have cross coupling if light in one waveguide couples over to the other via surface roughness. You might have autofluorescence, and a number of other imperfections are important to keep at bay as much as possible. Here is a paper I published with one of my students a couple of years ago. I should probably update this. If there's probably by now a better, well, it certainly needs to be a better table, but I'll check with this. So like take this with a grain of salt, but it's not so far off. I did update here some other things. So the material system of silicon in silicon dioxide, what we just looked at in the near infrared, has low photoluminescence because the band gap of silicon is, the band structure of silicon is indirect, so it's not a good for, it doesn't fluoresce. And moreover, if you work in the infrared, then the excitation of electrons in the conduction band is small. The losses nowadays you can get in good foundry processes like photonics or so, or IMEC probably, losses down even lower than this, maybe 0.1 dB per centimeter. But at somewhere like with that kind of structure, you can get a minimum bend radius of about 2 microns. So you can make really small structures because the refractive index contrast is so high. Whereas, for example, in silicon, the refractive index contrast is much smaller, and you have this like very large structures. So people sometimes compare, like they say, oh, but this material has a very low loss per, maybe it's like 0.1 dB per meter. So it's much better than silicon. Well, not necessarily, because a lot of the time, for example, in our case here, we're interested in what is the loss per gate operation, for example, rather than what is the loss per distance. So the per centimeter is just, that should not be the metric. Generally, is not the metric. Generally, you can take that, multiply it by the length of your device to get an overall dB figure, and that's generally the more important thing to compare between different waveguide platforms. In silicon nitride, for example, you can get very, very low waveguide losses. I think substantially even below this number of 0.1 dB per meter, but that's typically by deconfining the mode. So that means that the devices would take much more footprint. But for some things, if you want to do a buffer, for example, or a really good filter, that's fine. So lithium niobate here. So CJ might correct me. I did update this already. Is this still legit, CJ, of 0.4 dB per centimeter about? Okay, it gives me a thumbs up. Okay, very good. And there's a paper here that there you go. This is Marco Loncar's paper in 2020. It's a very nice paper to take a look at. And so there has been a lot of progress in these other material platforms, like in lithium niobate, and in CMOS compatible. This is something that we're now working on with Matt Eichenfeld down here, and CMOS compatible piezo optomechanically tunable photonics. A lot of progress in different material platforms that are pushing these metrics to a better place. And so, yes, silicon photonics, I think, is pretty great. And nowadays, you can actually design yourself a pretty sophisticated circuit I'll just give you sort of an outline of how you can make a photonic integrated circuit for, let's say, quantum or other things, really. You can start with the process development kit, let's say from Photonics. Then you can tape out the structure. It costs maybe some $5,000, I think, per millimeter square of area on a multi-project wafer run. And then you get it back and you will test it and you will find that you made a mistake. Generally, that's true, certainly for me. And then you will iterate. And after several iteration runs, you might end up with something like this beautiful thing here, which is a flip chip bonded silicon photonic circuit coupled to a electronic driver interposer via an interposer. This is an electrical interposer here, which is then wire bonded to the circuit, which has all of your drivers. This is actually not from Photonic. This one here is from IMEC. And I think possibly, yeah, so that's and so what you have here is a glued fiber array. Here you see the fibers, and they're in this fiber V groove array. And this here is a prism. So light actually from the photonic circuit through grating coupler couples out and then reflects off of this smooth surface into the fiber core. So, and this is a prism vertical grating coupler via prism fiber coupler. And then light comes in and out via these waveguide circuits. This is a nice way to like keep the whole thing a bit more compact and it's easier for packaging. All right, so that's the platform, and now we have the physical platform. I'd say silicon photonics in this case. What can we do with that? How do we make circuits that work in that? Well, actually, to give you a bit of an anecdote, in my group, starting around 2010, we were in a DARPA program where we promised to do some really great things in quantum key distribution, actually, in high-dimensional quantum key distribution, and that required a fairly sophisticated photonic integrated circuit. Because this high-dimensional quantum key distribution required that we not only use a 2-mode basis for encoding our information, but like a 1,000-mode basis, what the DARPA program wanted. Incidentally, if you have 1,000 spatial modes and excite only one of them with a single photon, you can think, well, how much information actually does that single photon carry? It's not just one qubit equivalent, right? Let's say you can think about this, well, how much information does a single photon excitation of 1,000 spatial modes contain? Okay, so for example, in our previous notation, I could write it this way. So I have a dagger, I'm going to excite one mode with a single photon, and I'm going to take mode J out of many modes, many waveguides, let's say, and there's 1,000 waveguides. And I'm exciting, let's say, the 57th one, in which case J would be 57. Okay, so that would let's get to one here. So it's hard to, again, like to see what the audience is saying, but like, most of you will have guessed, known the answer. The answer is, well, it's log, the information content is log of P times minus 1, this is log base 2, summed over all symbols J. Okay, this is the probability of sending in symbol J. So one photon, for example, in the first mode, one in the second mode, and so on. And since all the P sub J's are equal to one another, and let's say at maximum information, you would make all the probabilities uniform. Okay, that would give you the maximum information when you measure it. And that means that we're summing over 1,000 terms, each of which has a 1/1,000 probability of being the one that's excited with a single photon. And then that thing just simplifies to log base 2 of minus log base 2 of P, the probability of getting any one of these, which is 1/1,000. Okay, and log base 2 of 1,000. Okay, so the minus sign here goes in there and so on. And this thing here is about 10. So this is the DARPA program that wanted about 10 bits of information encoded on every photon. So actually, these photons, these are quantum states, and so you can represent many qubits in just one photon if you use a large basis. But it becomes exponentially large, right? I mean, if I invert this here and say, okay, what if I wanted this to be 20? Well, then you would need 1 million modes. Anyways, this is just sort of like, I'm telling you an anecdote. This is how we described the problem back then, using the physics that we have in this class covered thus far. And so we were trying to make circuits that were capable of manipulating single photon excitations over a very large number of waveguide modes. And that was the reason, actually, why we wanted photonic integrated circuits. Like, it's not we have to do everything in photonic integrated circuits. You have to have a pretty good reason to go that way. Otherwise, you should use free space modes. But we wanted to have a large number of waveguides. And so we set out, and we did several fab runs with foundries and other our own efforts in fabricating these photonic integrated circuits back in 2011 or so, 2012, to make these modal transformations on these high dimensional basis states. And the thing never worked. We could not get it to work. It was always there, the fab. So some people will say, oh, like the fabrication people just can't get it right. I think that's a fundamentally wrong statement. You need to, the fabrication people, yeah, the fabs will try their best, of course, and it's on the designer to come up with a good design that, that stretches the tolerances of the fab the least possible. Okay, and we did that also, and it still didn't work. So then ultimately what we figured is, okay, let's see if we can make a circuit that has a lot of redundancy and is programmable for all things we want to do, rather than having lots of customized individual circuits. Can we make a sort of like an optical field programmable gate array equivalent of a circuit? So let's get one thing really working well for the STARPER project, and then we can do all the subtasks with this one amazing circuit. And actually, like, it was pretty daunting to start out because we needed to have large numbers of like optical circuits. But actually, that turned out to be, I think, the right approach in retrospect. Although it took us a while to finally, it had to be sufficiently painful for actually for us to take that step, because if you want to make a modal transformation here, an arbitrary programmable modal transformation of, in this case, 6 modes in and 6 modes out in a unitary transformation, and you want to make it fully programmable, well, this whole thing here has to be described by some unitary transformation U, which takes 6 modes in and gives 6 modes out. So the number of degrees of freedom here is 6 squared. Or in general, the number of degrees of freedom is of order n squared for doing n waveguides in, n waveguides out, if you want to have an arbitrary programmable circuit. And so you will already say, hey, in your project, you said you wanted to do 1,000 modes. And that wouldn't work because 1,000 squared is 1,000,000. You can't have 1,000,000 phase shifters. And you're right, we couldn't get 1,000,000 phase shifters. We did the best that we could with spatial mode encoding, putting n up to about 20 or 30, and then used other degrees of freedom, namely frequency, to encode the other degrees of freedom. But anyways, this is just like how we ended up going in the direction of these programmable optical circuits. But there were a number of other groups that, for one reason or another, also were shooting in that direction. And we actually wrote together a review paper that is cited up here. Okay. And actually, in doing this, we found that, hey, actually, people had already tried to do this long time ago, back in the early 90s. And there's a paper here from Vreck and Zallinger, the guy who just got the Nobel Prize. They studied the same problem back in the 90s. And in this rather famous by now paper, they proposed how you could put together an arrangement of beam splitters and phase modulators together with some sort of a free space optical apparatus to make an arbitrary unitary transformation possible. Unitary transformation, linear optics, unitary transformation possible. They gave us a recipe. And here is that recipe. This is that recipe from these guys implemented now in like what we would in modern day photonic integrated circuits. And each of these blocks here is a Mach-Zehnder interferometer. Okay, so you have the input modes, output modes, and this is the so-called Vreck-Zallinger deconstruction of an arbitrary unitary linear optics transformation. But you see that this isn't the best way to implement this, because on a photonic circuit, I just said it's $5,000 per meter per millimeter square. So you don't want to have this dead space. You're paying for all this. And besides, it's going to be lossy a little bit. So actually, what's more favored these days is to make a programmable circuit that looks like this, the so-called Clemens decomposition, after Clemens, a PhD student at Oxford, who rearranged this, but it has the same number of degrees of freedom, but gets it in a smaller amount of space. Okay, more bang for the buck and somewhat lower losses. Cool. All right, and so that's basically what a lot of the programmable optical circuits for these linear optics transformations make use of, these kinds of shapes. All right, so what do these boxes look like? Well, here is a photograph of one of the devices that we taped out some number of years ago. And this is just what we talked about a moment ago, 2 waveguides coupled through a directional coupler. Here we have phase shifters, another directional couplers, and the output. So this allows us to move the quantum state, encode it here in a 2-mode basis, arbitrarily on the Bloch sphere. Yeah. So what's important is that if you want to access any region in that Bloch sphere, that how precisely can you get there? And actually, if some of these couplers here are not really 50-50, but if you have 50, like if you have 60-40 in the intensity splitting, then it turns out like you can think about it, you can work it out yourself, but it's pretty easy. But like what you will find is that there are some regions in phase space that you cannot rotate from one state to another. Okay, so there's these dead zones in the Bloch sphere. So you can't do a rotation to there. So that's limiting, and that's bad. And so it's actually it's been very important to us to find ways, and the community to find ways of getting these beam splitters really, really close to 50-50. But again, the earlier thing I just said, like you can't even, the fab does the best that they can, but it might be 49-51. And if that's already going to reduce the fidelity in your transformation, you should think of other ways of doing that. And I'll show you in a moment how we have gotten around that by using some more clever algorithms that can compensate for pretty large beam splitter imbalances. All right, so okay, so that's one of the boxes here, and then if we put all of these boxes together, we see this is one of our this was after several tape outs. This was the first sort of really functional photonic programmable integrated circuit that we were able to that really was enabling for us. This device, which we published on in a couple of papers, had 88 MZIs in 26 input modes, 26 output modes, and 176 phase shifters. And you'll say, wait, hold on a second. This is 26. You should have 26 squared phase shifters. That's how many degrees of freedom you should be using. And that's true for an arbitrary unitary transformation. Like with a small, it's a little bit smaller because of the unitary condition. But this is certainly smaller than that. And the reason is that we just couldn't get enough wire bonds to the circuit. And so we actually have some dead space here and here. And so recently we were able to fill that up. But it took many years of improvement on the circuit and on packaging and bump bonding techniques to be able to get there, to get away from this wire bonded chip. Okay, regardless, this is still some unitary. It can't do all unitary transformations, but it can do many unitary transformations that can be useful, and we can use it, for example, to take some input state encoded, for example, in the amplitude of these optical fields, 26 of them, and send those optical fields through this programmable circuit to produce an output state, whose value is equal to U times X. And that's been useful for many, many things, including, for example, some recent work here, this with the Yichen Shen and Marin Soljic on using these kind of circuits for machine learning accelerators. So yeah, I wanted to give you some insight. I don't normally go through this in a talk, but I figured it'd be good to look under the hood. So this is the pains of doing of managing packaging circuits with lots of modes. And these are basically, I should mention, these are thermal modulators still. So they're rather slow. So this is actually easier than if you were to do it with many RF fields. But nonetheless, it was difficult enough for us to do, but it's about as difficult of a wire bonding job as we could possibly take on at a university. So I said the phase shifters are thermal. So what happens there is that you run some electrical current through the waveguide through a heavily doped axis region. So here there's a current that goes through the waveguide. Here you see the cross section of that waveguide. Okay, we know how to make the single mode, right? Using our script. And here's the mode, in two-dimensional plotted here. And then so the current runs through here. And what you do is you make this doping of the silicon here smaller than the doping around it, so that the resistance here of this region is higher than the surrounding. So the current runs pretty unimpeded here, then the current has high resistance here, and it comes out the other end. That means that the power of the ohmic heating is deposited exactly where we want it in the waveguide. And so what you get is you can get like pretty compact devices, some tens of microns of length required to get a pi phase shift controllably. And the losses are good, but the speed is only like sort of microsecond scale that you can switch these things. And yeah, and you have heating and pretty like to keep a phase shift, you do have to maintain a couple of milliwatts per phase shifter. So if you have, like in our case, a few hundred phase shifters, that's fine. Okay, like the overall number of the power is maybe sort of like still below or near a watt, and but that's not going to work for cryogenic applications, for example, because you would be battling your cryostat pump. Fortunately, though, there are ways to use silicon photonics at cryogenic temperatures with phase shifters, and one of the ways, there's two primary ways, I think, two particularly good ways. One of them is MEMS, and the other is to make silicon electro-optic. So naturally, the silicon does not have a chi2 coefficient, but you can induce one if you look at the polarizability of silicon, and you look at the polarizability term with the third order, so chi3 multiplying the electric field. Okay, so this guy, and if you plug in here a DC offset EDC that's applied by the reverse biasing, for example, across a junction across the silicon waveguide, plus maybe here an electric field that is AC or perhaps even optical. Okay. Now, if you expand out this third power here, you get to first order, you will get a term that goes as chi3 times 3 times EDC times E optical squared. Okay, so this term looks exactly like the chi2 nonlinearity term if you set 3 chi3 times EDC equal to chi2. So that's the effective chi2. So that's what's used here, and so you can in fact get, by this kind of strong electric field bias, you can get cryogenic modulators in silicon photonics that actually can be very fast as well. Or you add materials. You can add like electro-optic polymers, or people are integrating other electro-optic materials like thin film lithium niobate or BTO or so to the silicon structure. All right, so that sort of like adds to the capabilities of the silicon photonics platform. You can do more stuff. People do more stuff. Let me clear this page. Okay, so, and yeah, so for example, like if we looked a while ago at this boson sampling experiment, now suppose you could have a boson sampling experiment, but actually on a programmable unitary transformation rather than the one that's given by assembling these macroscopic Lego blocks that were done in the group of Genway Pan. Now, for fairness, it's still the case that these kinds of silicon photonic circuits are lossier than the bulk optical components that they used, and that's certainly one of the reasons why they didn't yet use them. So there's more work needed in making the losses lower. Okay, so how do we couple it to it? I think we covered some of the stuff already in the regroove and the grading couplers. Here is so these programmable circuits. They, you need to like have the photonics, but that's really just part of it. Like a lot of it really deals with making an optical, good optical interfaces to fiber, let's say, and also to make good control electronics. So I think I'm gonna skip over. Oh yeah, no, this is actually important. So here, because like if the directional coupler isn't sufficiently reliable to be 50-50, what you can do, one of the things you can do is what they did here in this paper. You can, rather than making a Mach-Zehnder interferometer out of two directional couplers, you can add a segment here, which can, if the errors between these Mach-Zehnder differameters, that you can cancel out the errors, provided that they're correlated. Actually, if it's 5149 here and 5149 here and so on, then you can cancel them directly to higher and higher order. Here's another device that we make, these tunable ring resonators. Here you can have a ring resonator whose quality factor and center frequency is individual tunable. And by putting all these devices together, various groups around the world are making more sophisticated programmable photonic circuits. And here's just a compendium of a few of the earlier ones. This is interesting for some initial quantum work, like, for example, looking at, like here, this work here was a very proof of principle work towards simulating the vibrational quantum states of molecules, but this doesn't yet give an actual practical advantage. But it's kind of like showing what might be if you could have larger systems. So just a side note here on algorithms for error correction. So as we thought about making these optical circuits bigger and bigger, it was becoming more and more apparent that just asking the fab to be more and more precise wasn't going to work, and making the circuit bigger, like making it twice as large of a Mach-Zehnder out of like, as I showed a moment ago, would also add significantly to the loss. Then we started really to get into photonic hardware error correction. And it's an interesting thing because when you think about like the Babbage difference engine or for something like this, one of the early computers, it never could work because of the buildup of errors. But optics is different, because if you have an error upstream in your optical circuit, you can cancel it in principle downstream because it's all coherent. So if you have a phase mismatch early on, you can have it canceled later on in an optical circuit. So optical systems, in terms of like making perfect or error corrected systems, are fundamentally different than like than mechanical computers that have been considered in the past, at least. So that's giving us hope. And in fact, so we have a series of papers here that show that error correcting is possible in optical circuits. I should also point to very nice work, in particular from the group of David Miller at Stanford, who also he and his team continue to refine, to contribute here to the algorithmic approach to hardware, to making hardware more error resilient. So in particular, we showed in this paper that if you program this kind of Mach-Zehnder mesh appropriately, you can reduce the error that the gate error. Okay, so again, looking here at the gate error would be defined from the expression for the fidelity from the density matrix that we had earlier on. You can reduce that error from order epsilon to order epsilon squared by just an algorithm that sort of cancels errors using a local rules, which are also easy to implement. And that's in that paper that I just flashed up there a moment ago. And this paper, if you want to take a look at that error correction algorithm. So yeah, and here's a compendium of recent work from the community on making quote unquote perfect programmable optical systems out of imperfect hardware. The fab can never be perfect. And so at some scale, it will always destroy you. But if you have some error correction schemes, you can live with it asymptotically. In fact, we showed in this paper here by Ryan Hammerly that asymptotically, we can cancel errors perfectly in the asymptotic limit of very large optical circuits. You have sufficient redundancy to cancel errors entirely. Errors due to phase mismatches and beam splitter imperfections, not errors due to loss, unfortunately. So now I want to talk a little bit about quantum light sources and detectors. So far we've talked about how to transform the optical modes using these like the optical waveguides and so on, how do we actually excite a quantum mechanical state as the starting point? Like when we talked about the Hong-Ou-Mandel effect, for example, and other examples, like I just said, oh, suppose we start out with a vacuum state of like some number of modes, and then easy breezy, I just put in a single photon at mode J. It's as easy as putting a dagger J in front of my state ket. Well, it ain't that easy. In reality, experimentally, we don't have that. Like, we don't have a perfect way to initialize the state. So what can we do? So a couple of ways are illustrated here. So one is you can use spontaneous four-wave mixing in silicon, for example, where you take silicon and you excite it with a pump field in the telecom, for example. So like say this is 1.5 micron worth, about 0.7 electron volts, 2 times 0.7 electron volts, 1.4 electron volts, then decays into an idler and signal photon whose energy has to add up to that of the pump. Okay, but that can happen different ways. And if the different ways that this can happen are coherent, then you can get an entangled state for the idler and the signal photon coming out. And so that's one way that you can create non-classical states. For example, if you want to then have a single photon, you could herald on one of the photons. Suppose like you have a detector in there that splits out the blue photon here, measures it, and then you know that you have one red photon remaining. Then you would have that kind of an operator, a dagger, okay, on the signal. A dagger signal would be applied to the mode in which you have heralded the idler. Okay, that is one way to initialize this state. But how well you do it, okay, is it a pure state? No, it won't be a pure state because your detection is imperfect. So what you actually have to do is use a density matrix description for it, because there's some classical uncertainty in the detection apparatus and stuff like this that's not perfect, that you must take into account. And so you look at a density matrix, and then you try to make that density matrix as pure as possible. Other ways are, for example, to use Chi2 processes, okay, but they are essentially the same thing. They're heralding methods. You can do deterministic single photon generation. You can apply that A dagger J deterministically, in principle, using an atom. You can excite an atom deterministically by a short coherent optical pulse. That is to say, a pi pulse. We'll put an atom from the ground state to the excited state. That is to say, the electron is now in the excited state of one of the levels, and then it will decay after some time and emit a photon into the mode, let's say, with some probability. So that is a deterministic single photon source. So how good are these guys, these deterministic single photon sources? They've come a long ways from the first demonstrations of solid state single photon sources here from Peter Mischler. This is one of the very early ones. This is showing me here the probability that 2 photons are emitted from this atomic system at the same time is sharply reduced to the probability that they are emitted, that one photon is emitted at one time, and then again, a reset time of the atom, in this case, about 13 nanoseconds later. So this is called the photon purity, and you want to make the photon purity be very good, which corresponds to second order correlation function being near 0. People have actually, in the meantime, gotten this very close to 0, to 0.005 or so percent. Okay, so 10 to the minus 4, 10 to the minus, maybe I think 10 to the minus 5 is sort of like is one of the best values achieved these days. So they're very good. Unfortunately, they're not efficient enough yet, and they require special cooling and so on. It's still work, definitely a lot of work to be done. But things are getting better. At the same time, you could go back and like try to make these heralded single photon sources better, perhaps by ringing up the cavity field, ringing up the pump light into a cavity field like here, so that you can use less power per waveguide to get a decent brightness. And so that's one of the approaches that people take. Ideally, you would also integrate into the same circuit the superconductor, like some sort of detector, single photon detector. That still remains very difficult. People have been working on this for a very long time, and it's very difficult to get sufficient isolation of the pump light, which can be 16 orders of magnitude or so brighter than the the down-converted light or the four-wave mixing light, it's very difficult to isolate that sufficiently. So that's still very challenging. Okay, but if you have many imperfect and heralded probabilistic single photon sources, heralded by using some detection on the idler mode, for example, then you could say, okay, like if I have a switch, maybe I can just multiplex them together. That's another way to do it. But unfortunately, so far, the switches are not sufficiently efficient that that you get any net advantage out of this. Okay, but nonetheless, some interesting work going on there towards that direction. And so here's recent work also in this in a different state preparation. This here is a on-chip. This here is showing on-chip interference from a single silicon ring resonator source. So here there's some clever techniques you can apply to bring up multiple rings so that you can just by passing the output of these two rings, these two spirals in this case actually, into linear optics, you can actually produce this Hong-Ou-Mandel state. But still, you can produce this Hong-Ou-Mandel state that's shown in this paper, but it's still difficult to know when that happens. Because if you want to preserve and use this Hong-Ou-Mandel state, you have to herald it. And so you need some sort of ideally a quantum non-Milesian measurement of this thing. And of course, you should say when you're designing these kinds of things, like how good is good enough? What do you have to do? And so I have a slide here that you'll have in your shared notes that shows the source requirements for different kinds of applications. In case of quantum key distribution, actually, that's all optical quantum key distribution, actually the requirements are rather forgiving on the purity and so on. And a lot of this stuff can basically be absorbed into the error correction codes. But if you want to do things that are more demanding, like what we had on the second slide on cluster state quantum computing, things have to be very, very good. So I think some of the companies might be leading the charge there, like we should look out for what PsiQuantum are doing, but it's a pretty tall order. Okay, so any questions up to here? CJ, how much time do we have left? Like a half an hour? Yeah, half an hour, okay.
Yeah, half an hour.
Okay, so let me ask you one question. You're like, see, like, for example, so one of the problems with silicon is that you have two photon absorption. If you want to have a bright entangled photon pair source, you can pump the waveguide strongly, but then what happens is that you get occasional two photon excitations of electrons into the conduction band. That in and of itself isn't bad, but when that happens a lot, then you have a lot of free electrons that can couple to the optical field and cause a lot of absorption. So this can be a quiz kind of, any ideas for how we could reduce this problem of two photon absorption due to reduce this problem of additional losses through two photon absorption? All right. I will reveal the answer. So what you can do, for example, is reverse bias. So if you do generate a two photon absorption created conduction band electron, you try to sweep it out as quick as possible. Okay. So let me see. I want to get to the detectors. All right. So I've been kind of like here, just filling out the toolkit on these integrated circuits. Like we've been saying before, it'd be nice if we could detect with lowest possible losses and latency. So then you'd say, hey, we should try to integrate detectors on chip. So a bunch of groups have tried that. I think maybe one of the leading groups is probably the group of Hong Tang. They've done some very nice work. But it still is very difficult, I would say, to get the electronics and the optical systems to work simultaneously, the dynamic control on the optical systems, as well as the detection to work so that you can measure and then perform some feed-forward action in a time sufficiently small to maintain coherence of your quantum system on the chip. That is still a very difficult thing. Photons do not live very long on photonic circuits, nanosecond. So we address this problem in one way, for example, by pick and place transfer, but there's several other techniques, for example, like growing, depositing superconducting film and then patterning it into the single nanowire detectors on top of waveguides. Okay, so you have the single photon sources, the single photon detectors. What else do we want in our toolkit to be able to do the stuff that we started out talking about here? Well, we want memories for quantum networks especially. And so there's a wide choice of memories that people are investigating. And particularly in the CQN, of course, we work on color center based and diamond memories. And then of course the question is, well, how good do they have to be? How many do you need, and so on? So you should look at blueprint studies that give us some indication of that. Like, do we need 100? Do we need 1,000? Do we need 1,000,000? Can the errors be 1% of a rotation error or 2-qubit error? What do we have to do? So to this end, we and others have done various studies. It's useful to look at these things so one can get a sense of the scale of the problem. So for example, just as a benchmark of what would be sort of a practical quantum advantage, because so far we've only had quantum computational advantage for, as far as we know, not useful things. They're not utility based. It'd be nice to do a utility based quantum advantage, which hasn't been demonstrated. One of them would be to do 2048 bit factoring. That's certainly not possible as far as we know with classical computers. It's a well-studied problem. And if you could do it with a quantum computer, that would be a pretty clear case of doing something useful. So how difficult is that? So it turns out when you look at the resource requirements that you need in order to do this, you need to do factoring of n bits, you need of order n logical qubits with some multiplicative factor, basically. Maybe a couple, like 2n, for example, is one type of algorithm, has twice that. So you need maybe 5 or 4,000 logical qubits. But given the error rates that these gates have let's say that the error rates get better to 0.1% or so, 2-qubit gate errors, then that would result in a physical qubit count of about 10 million. So that's the kind of problem you're looking at that one wants to, we have to solve to make practical use of these kinds of quantum machines, insofar as we know. I mean, there might be an intermediate scale quantum computer application that surprises us, but as far as we know, we have not found such a thing yet. Okay, so let's take a look at the different kinds of solid state emitters in solids. And so here's a listing of some of the leading color centers in solids, not just diamond, but also silicon carbide, for example. And you can pick your favorite, one that matches the waveguide architecture that you want and has a reasonably good error performance and so on. And so in our CQN, of course, we are going with the silicon vacancy center, although that requires quite high, quite low temperatures to operate with long coherence time. There's also a lot of interest in using heavier group 4 elements like the tin vacancy. We'll see. And then you now with that, we have sort of completed the quantum optics toolkit. Namely, we have the switches, we have the linear optics, we have the, in principle, we have a pretty good quantum memories and and detectors. So these things have become very good in isolation. It is still a very big challenge to put them all together in a system that maintains their properties that have been shown individually. And this is one of the big tall orders, for sure, in the CQN, is that we can sort of find ways to get profs and, especially the students and postdocs from the teams to work closely together so that we can make these interfaces work efficiently. So just to give you a sense of what we're doing as part of the CQN here with other team members, this here is a CMOS circuit produced at a large semiconductor foundry. This here has 1024 diamond waveguide, which has a few color centers. We're taking this route because the end goal is that we need to have very large numbers of qubits as far as we know. This is why we do. It's not fun. It's pretty difficult, but as far as we know, we need to get to millions of qubits. So that's the approach that we're pursuing in these efforts. So at this point, there's a Jupyter notebook, but I think I'll skip over it for the purpose of this quantum communication demo. So one of the early applications of quantum networks is quantum key distribution. And quantum key distribution can be done in a number of different ways, either just sending photons or photon alone quantum key distribution. But that's limited in how far you can go by how far a photon can fly, roughly. So maybe 3 times that. So like a few hundred kilometers. If you want to go beyond that, as far as we know, so far, the only demonstrated experimental method is to go beyond that loss boundary is to use quantum memories. And so I think I'm just going to skip over to that. So that's kind of like cutoff between so-called repeaterless and repeater-based quantum secure communication is shown here. This is showing the distance converted to loss by 0.2 dB per kilometer, roughly, versus the secret key rate that you can obtain by various methods. For example, the BB84 scheme, the single photon BB84 scheme, assuming that you have a perfect single photon, so it's actually not bad. But you can only do so well. Like this red curve here is showing you the best secure key rate that you could possibly achieve just theoretically by the decoherence of the photons into the channel given by the loss of the channel. So if you want to go to the other side of this boundary, if you want to go to 200 kilometers at a not ridiculously low rate, you have to beat this red line. And that fortunately was done some time ago. Here's some circuits that I'm showing from that actually have made this QKD systems better, the linear optics QKD systems. But I want to get to this part about bringing memories online. So to realize this vision of connecting qubits at a large distance, thousands of kilometers, as far as we know now, the only experimental systems that could do that are memory-based so-called quantum repeaters. Although maybe the optics will get sufficiently good that one can do forward error correction on the optical mode. That's very exciting, but it's not been demonstrated. But quantum networks with multiple diamond color centers have been demonstrated, and one of the leading ones is based on diamond nitrogen vacancy centers, which are entangled by spin-dependent optical transitions to the electron spin in the diamond. Then you measure the optical fields from the diamonds emitted, for example, or scattered on a Bell measurement apparatus like a beam splitter followed by 2 photon detectors. The heralding signal here tells you that a photon was emitted by one of the 2 qubits, but you don't know which one. This Bell measurement here has an erasure step through the beam splitter, and that produces a heralded entangled state of the electron spins, for example, which you can map by hyperfine interactions to the nuclear spin. And then repeat that using the freed up electron spin with another memory down the line. This is essentially like all the elements of what we are trying to do in the Center for Quantum Networks, to propagate entanglement over long lines in a heralded fashion, sort of divide and conquer approach. And indeed, in some very nice work that came out a couple of years ago, led by Mihir Bhaskar and supervised by Mikhail Lukin at Harvard, they were able to reach a point at which the, like for some area in the parameter space, they could do better than the losses themselves permitted. Although the approach did add other losses, so there wasn't yet a net benefit, but it did show a very important thing that given some loss, you could do better than photon alone using a quantum memory. And so that's what, of course, in the CQN was one of the starting points for our program, is to bring that, to build that out. And And so here to give you a sense of what actually one of the approaches are that actually takes these different things together that I showed you the different parts of the toolkit. This is sort of a decent representation, I think, of the various approaches that are being taken. So, okay, what they have in common is some sort of a spin photon entanglement, electron spin in the color center, 2-photon entanglement using the optical transitions of the color center. It's useful to enhance that by sticking the atomic system into a cavity. Why? Because if you think about what we talked about a little while ago, let me see if I can. So why do we do this part here with the cavities? A lot of stuff going on here. So if we think back to the discussion on the electric field the vacuum field, right? When we looked at what are the vacuum fluctuations in a cavity, we showed that the vacuum fluctuations, like the electric field fluctuations, if the cavity has a Fock state of 0, there were nonetheless fluctuations in the field, like RMS, electric field RMS, was proportional to 1 over the square root of the mode volume, right? That's what came out from our exercise towards the beginning of this long workshop. So this shows that, since the spontaneous emission rate depends on the dipole moment and the vacuum fluctuations, and the dipole moment of the transition is fixed by the atom, what you want to do is to enhance the spontaneous emission rate into the mode that you care about, the cavity mode. You want to make the mode volume small. And so that's why there are these photonic crystal cavities here to get a small mode volume. Okay, that's explained by that theory. Okay, so yeah. And okay, so the next thing that's happening here is you see in this artistic representation by Michael Walsh, there is a color change in the spins. And the reason actually what it means is like the optical resistance actually changed a little bit. And we do this because not every atomic transition is identical to another, but we have to have the photons be identical, because remember, for this Hong-Ou-Mandel effect to occur, the 2 photons had to be indistinguishable. The symmetry of the initial state was critical. So to ensure that, we have to make the optical wave packets be identical as well. And that's why we needed that tunability. Okay, next up is our Mach Zenith interferometer. Now, this one is a weird one in this case, a bit unusual one. This is based on a strain-actuated silicon nitride Mach Zenith interferometer. That's because in this scheme, we need things to work at the visible and with virtually no power consumption, because this has to be in a cryostat. So one of the ways to do that is using that technology. The other leading one probably is to use lithium niobate, like what CJ is developing, and some of the people in my group, and through collaboration actually with Marco's group. So that would be the Photonic Waveguide platform. Now here it's important that these photons that finally make it past this beam splitter here, which is our erasure step, right? They be detected with sufficiently high efficiency, with reasonably high efficiency. And for that, once again, it would be pretty awesome if one can get the detectors directly on the chip. So far, we have to bring it off the chip, which adds a lot of additional loss. And because the heralding is less frequent, that means the entanglement is less frequent. But that gives you sort of an overview of all the different parts that are in fact coming together, fortunately, as part of the CQN. All right, so let's see. So to get to really long distance networks, we need lots of qubits. We need like high efficiency links, and we need some way of optical management of lots of qubits, which in turn will probably need some sort of a programmable photonic system, such as these photonic integrated circuits. Hey, but if you want to go long distance and maybe not go through fiber, we don't have to go through fiber. Maybe you can take some wrong hops, perhaps using a satellite link, and that's also something that people are considering as part of the CQN. But then you quickly find that you need a different kind of entanglement scheme if you want to do that thing. And that has stimulated some work that is now a big collaboration inside the CQN, including with Mike Raymer, for example, on building a new kind of entangled photon pair source that is heralded. And if you had a heralded entangled photon pair source that is at the right wavelength, then you can, it turns out you can get a very big advantage in the entanglement rate of order of the 1 over the square root of the transmission that you have in the channel. And since the transmission is small, the 1 over the square root of the transmission gain can be large. And so a lot of work going on there. And this is basically using these. So one of the big opportunities here is to use these kinds of spontaneous 4-wave mixing or 3-wave mixing sources that we had maybe 20 slides ago or so on photonic circuits that allow you to do the different functions that we need in terms of pair generation, but also routing and other functions over multiple modes at the same time. Okay, and I think with that, I'm basically at the end of the quantum networking section. But I did say early on that the quantum networking is inseparable probably from quantum computing in the long run. So I just wanted to show a couple of instances here on where they connect these kind of optical circuits that we're doing for quantum networks, how they connect with quantum computers. One of the ones, again, I think is sort of like, again, with so CJ is working on in terms of if one can optimize the coupling between 2 optical fields using a Chi2 or engineered Chi2 medium, then one might be able to make deterministic gates between photons, and that, for example, for these entangled photon pair sources would be really transformative. Okay, it would give us a huge speed up in the rate of the entanglement generation over a quantum network. And that in turn would allow you also to make better quantum computers, because if you can connect quantum computers more efficiently together, then you have more freedom at designing, for example, at choosing your error correction methods. And then I showed at the very, like one of the early slides was also about using optical systems for quantum control of, rather than carrying quantum information, just to control quantum information that's like sitting in atomic systems. There's a lot of progress there, I would say, as well. And I think with that, maybe CJ, so we have about 15 minutes left. I think maybe to allow for some discussion, we could. Let me just maybe roughly. I'll begin to wrap up here. I guess one thing that people did want me to talk about is this thing here at the end on spatial light modulators. So when you think about where today's technology is, you have on the one hand high-speed optical modulators, but few of them. Like, telecoms uses single modulators, or perhaps a dozen or so in an optical system. But then on the other hand, you have slow, but very many modulators on, for example, spatial light modulators, like liquid crystal devices. There you can have millions of channels, but you can control every one only at millisecond timescales. Really what a lot of these things in quantum need is something that does both high speed and large channel count. And this has motivated several people. This is not a revelation. Certainly, there are a lot of people have tried to make high-speed spatial light modulators, but it's been a really tough thing to do. And so, I think so like one pretty promising direction I think that we've even taken is to make arrays of silicon cavity modulators, where actually nowadays on a chip this size, which incidentally I have standing up there on the, I don't know if you can see up there, that's one of the wafers. It's a 300 millimeter wafer from AIM Photonics that or from the Albany fab that if you filled it up with modulators of this type would have 20 billion modulators. So they can have a lot of modulators there still is significant work to be done on the controlling of these large numbers of modulators, but definitely it's an incremental step towards very large numbers of spatial modes of control. And with that, you can make some pretty cool things like a very fast display. This one is not a very high resolution display, but like I said, there is nothing else out there in the realm of high speed modulators with many modes. So here you can do an SLM, and this can actually like operate with gigahertz switching speeds. Another hope is that other demands like this sort of this renaissance of computing, the other thing was the machine learning. And maybe the machine learning, well, surely the machine learning as we see it already is contributing to build that platform of large numbers of modes, high speed, and large numbers of levels of control. That's being motivated also by making machine learning accelerators. But it would be, the requirements actually are very similar, or maybe identical in many respects, to what we need for large numbers of controllable quantum modes. And so, yeah, I think with that, maybe for students also, I think just something that I've learned, maybe a life lesson here in the end, is I said the struggle that we had with this DARPA project of doing, these 10 bits of information per photon and like very large numbers of modes and so on. It was a struggle to and like, sometimes it like looked pretty bleak, like, oh, we're never going to make this work. But then it's exactly at that point when you can make a real impact. When you see something that's really hard because you've tried it a lot and it still isn't working, but people care that it works, then you know that you've got something, right? Then you know that you're onto something. And then if you persist, and like my experience has been that persisting generally has, I would say every single time actually has worked out, either in giving more knowledge, useful knowledge, because when it was in an area of parameter space in research that hadn't been trodden before, maybe not practical device, but a useful knowledge, or sometimes both. So yeah, keep going. All right, I think that's all I have really. That last bit here is on Outlook, but I think I'll skip over that. But yeah, so in the slides that will be that will be shared with you, you will have a bibliography on some of the stuff.
Dirk, there's a question about SNSPDs in the Q&A.
Okay, so instead of superconducting nanowire for detection, would it be possible to use topological insulators since they have zero resistance surface conductivity? I think, okay, if I understand the question correctly, so let's say the superconducting nanowires work by, you have some small cross-section wire of superconducting material through which you pump an amount of current that is close to the critical point of the superconductor. So that when a photon comes in and creates a small resistive region, the current is crowded out into an even smaller cross-section, which then creates a current density greater than what the superconductor can support, and you get a hotspot and it grows, and that's your signal. If you had a topological insulator, then my concern would be that exactly the topological nature of that thing could make it maybe be counterproductive. But I'm happy to talk more. But like it could be counterproductive because the expulsion of a current where the hotspot happens in the topological insulator would be the current would just flow around that area where the hotspot is created. But I suppose it would still lead to current crowding. So I don't know. I'd be happy to talk about it more. I'm not sure. Also, I would say I think that there's a lot of other techniques that people just aren't exploring yet that are not superconducting at all to do single photon detection in the infrared. Up conversion is a good one. Like, again, I'm pointing a lot to CJ because I looked at her papers recently, and she's there, so I have to. But like, hey, if you can make the nonlinear optics work well in lithium niobate circuits, and you can efficiently frequency up convert, then you can pass the problem to a silicon single photon detector, right? So people have done this already, but not in an integrated way. So there's actually one shouldn't get, so like this very good thinking. Great question. And I think it says more broadly, the lesson here that maybe Jack's point teaches us is we should think widely, because there's only a little bit of physics has been explored for this purpose. So Matt Brown says, is there any reason why one could not or would not want to grow or deposit an SNSPD at the end of a waveguide on the chip beside the downside of needing cryogenic temperature? That is so absolutely correct, Matt. People do try to do that. The question is, so I think it's, again, that the problem there points to things are one can do things reasonably well in isolation, but doing them together compounds the difficulty. Like if your process has a probability, after you try really hard, of yielding at a probability of, say, 50%, all right, then you throw away, you take every second one. That's okay. But if you have other processes which in themselves are also still pretty low yield, and superconductors unfortunately are among them, then you have a problem of this compounding of yield problem. And I think that's a big part of the issue. It's difficult to monolithically integrate things. I mean, even for the most advanced semiconductor manufacturing houses, monolithic integration is hard. But we also see great success with heterogeneous chiplet integration. A lot of companies like AMD are actually doing exactly this. They use many low-yielding devices. They can pick and place them, and then they integrate things by some pick-and-place process, heterogeneous process. And so I actually have a lot of hope for that. And incidentally, in the CQN, we just got a, well, not funded by the CQN, but if people are interested, we just got a pick-and-place machine at MIT that's one example of like how the promise of that heterogeneous integration technology. But then to Matt's point, yes, I think then if you could just stamp detectors where you need them on a chip, I think that's more likely to work.
Yeah, maybe I can chime in a little bit.
Yes.
on that aspect. So this is something that people are actively looking into, and like Dirk said, it's a kind of a yield compounding issue, and like a major issue with this is kind of a fabrication. From what I know is that the fabrication is really challenging. Like Dirk said, putting superconductor on the material is not exactly straightforward, and for silicon processes, a lot of places won't do it. For other stuff like lithium niobate that I work on, some of the superconducting fab processes are not compatible with, let's say, the lithium niobate etch process. Nonetheless, a lot of work has happened here. Dirk, you probably know a lot more about the silicon side. But for superconducting nanowire integration on, like, let's say, lithium niobate photonic platform, people have done it at MIT with at like Carl Bergen's folks have doing it, and then in Europe, like Wolfram Pernice and also like Wolfram Pernice has done it, and also like
the company
at Paderborn, Tim Bartley at Christina Silberhorn's folks are doing it. So it's something that people want to do, and it's useful for like various things. It can help with some superconducting heat load issues as well. It's just hard to do fabrication wise. Yeah.
And they started a company, which is another, I think, important lesson. You've got to build an ecosystem. So at some point, I hope that one can buy like the stampable superconducting detectors, just like what CJ is, CJ is referring to. But if there has to be sufficiently good supply chain effectively, so that you can assemble all the different parts to make something that's useful. Like in the car business, right? A couple of like just a chip shortage ground the whole auto manufacturing stuff to a halt. So there are a lot of things that have to work simultaneously, and so yeah. If I'm very happy, for example, that the Pernis group, together with some collaborators, I think at Delft, starting this company, because we need intrepid entrepreneurs to take what's in the lab and actually make it reliable and useful at scale. Only then, I think that's a prerequisite to making complex systems work. Okay, well, this was a long winter school, I believe. There's a lot of stuff.
CJ, Dirk, thank you so much for taking the time to put together the materials and present them today. For everyone who attended, thank you for taking time out of your busy schedules as well. We will have the recording and supplementary materials available next week, hopefully, but those will go out to all who were registered and attended. And I think from there, are we good to end the session? Awesome.
Okay.
Thank you all. Have a great weekend.
Everybody else. Okay. Yeah, indeed. Have a great weekend. See you.